Now we go back to current slide. Okay. I was just saying, sorry I have to repeat this, I forgot to turn on integrity, screencast-o-matic. The first several types of erosion, you might say, that we've talked about, they're not all erosion, but remember we talked about soil creep, which is the slow movement of soil down a hill due to gravity. Landslides, which is rapid or more rapid movement of soil down a steep hill. That's gravity driven. Water erosion, gravity driven, though other things it influences other things like chemical reactions and other things like that. And then glaciers even are gravity driven. They're just driven very slowly. Okay. But now we're talking about wind, and wind is the one erosive feature, you might say, that is not gravity driven. And Shelby's here. Okay. Now, wind also is considerably less efficient than water or ice. Can anyone think of reasons why? Why would wind be less efficient at eroding, which I don't count that as an efficiency issue, than either water or ice?
It doesn't really have any substance to it. Like
okay, getting pretty close. There is substance there, but two things. Remember the two phases of erosion: detachment, transport. Okay, something has to detach the soil particles, and then something has to move them.
Isn't it usually like rain that transports them all around?
Exactly. So you're both hitting right close to it. Energy is involved in both of those processes, to detach the soil particles from the structure they're in and also to move them. Okay? Energy, specifically kinetic energy, is 1/2 mass times velocity squared. Okay? Now, let's talk about water erosion, liquid water erosion. It has mass, and the faster it moves, the more it erodes, okay? Because you're squaring that velocity. Glacier erosion, the speed is really slow, but the mass is really heavy, okay? So that's why it's pretty efficient. Wind, however, and this is what I think Brandon was talking about, wind is the mass is very small. Very, very small. So even when it's blowing very hard, like a high velocity, you still have such a low mass. That's why wind is usually a lot less efficient than water or ice. The energy that wind can generate, the kinetic energy, just doesn't come close to usually what water and ice. Two major processes, okay, for wind. The first is called abrasion, okay? If you have been out on a very windy day, and I was in Nebraska and I really felt this pretty badly on cold, windy days, I swear it felt like that wind, especially when little chunks of ice were in it in the wintertime, was literally chopping away at my face, okay? It really wasn't, but it felt like it was. That's abrasion. Sometimes this is called natural sandblasting. If the wind is picking up grit, that's usually silica, quartzy material, which is really hard, and whamming it against a surface, then it's going to break away that surface. Abrasion, natural sandblasting. It produces what they call ventifacts. Of course, venti means what? Okay, vents, think of those. Ventilation, exactly. So this is wind-driven, so wind-driven artifacts, basically. In other words, what are the results of wind erosion? Okay, and here's one of the ventifacts, is that if you have a predominant wind from a predominant direction, and most of us have that, the vast majority of our winds come from the west. because of where we are on the globe, okay? I should bring the globe in. I hadn't thought about that for today, but I probably should have. We have a prevailing westerly winds, okay? And therefore, a rock that's over here is going to be hit by winds from the west side, more so than from the east side, or north or south, usually. So therefore, you're going to have sloping happening here because this is going to wear away that original shape of the rock and make it this way. Now, if in a certain location you get a change of direction and you have predominant wind from a different direction, then you could start having some wind effects coming from the other side as well, okay? That would be features of the rock that are caused by the wind. Vent effects. Vents are artifacts caused by the wind. The shape will depend on the prevailing winds, and that's what I just was describing. So there's the first one, abrasion. The wind is blowing particles against, usually sand particles, against the structure, whatever it is, the rock, whatever. The second is deflation. The loose material that is knocked off then is picked up and carried away by the wind. There's your transport. This is your detachment. This is your transport. Same two principles before, just with wind we usually use different titles. Abrasion for the detachment and deflation for the transport. But guess what? The particles picked up here and carried off, they hit the next rock and they're part of the deflation. The abrasion. So it's an ongoing cycle. Okay? Now, if the wind is picking up these particles and moving them around, which it is, then when the wind does slow down, just like the the moving water, when the moving water slows down, the sediments fall out. When the wind slows down, loses some of its velocity, meaning energy, it can't carry as much stuff. Well, then the wind-blown deposits, things that deposit out, just like sediments deposit out, the wind drops the things. One of these are called the dunes. Low mounds or ridges of sand or other sediment that has been dropped there by the wind. The wind finally lost some energy, dropped them out there. And this happens a lot near the ocean. You have the sand dunes. Now, those probably were somewhat contributed to by the water bringing up the sand, but then wind picks it up and drops it in dunes a little bit further inland. Now, this is largely sand or other sediment. But another type of wind-blown deposits is, strange-looking word, is pronounced loess, L-U-S-S, is how it's pronounced, but it's spelled L-O-E-S-S, okay? This is fine dust that's deposited over a large, large area. Can someone think of a period in our history where we had this kind of problem? The Dust Bowl. What had happened that brought the Dust Bowl about?
They kept using the same crops to keep them.
Okay, very good. Especially in the Midwest. When we were discovering this country, the continent, and moving westward, man, they found that rich, rich, rich farmland there in the Midwest. Okay? And a lot of that wasn't farmland at the time. What was it called? The what? The plains, exactly. And they had another word too, the prairie. Okay? Wasn't used for farming because no one was out there farming. Most of the people out there were the Native Americans. We call them Indians. They weren't that big of farmers. I'm sure they did some. What were they primarily? Say again? Hunters, yeah. Hunters and gatherers, exactly. Now, what was one of the big game that they hunted? The buffalo. But also deer and other things like this. Those were grazing animals. And fortunately, the Great Plains were just covered with this fantastic, nutritious because they're such rich soils. Thank you, Canada, remember? Prairie grasses, okay? And what made prairie grasses so well suited for the prairie is they had extensive root systems. I mean, those roots went way down, and they were pretty good, nutritious grasses. And that's what the buffalo lived on, the elk, actually they're not buffalo, they're bison, but the deer, the antelope played, all that kind of stuff. So, here we came out, and we're discovering this, and it's just, I don't know, happenstance of fortune. We happen to be moving out there in a relative rainy period. So here they had found rich soil, they found nice amounts of rainfall, and they said, boy, can we ever grow the corn or the wheat. I don't think they had started soybeans yet. This looks perfect. But we got to deal with these old prairie grasses. So basically, they dug them up, they burned them up. Now actually, they had another pretty useful use for them. They built the homes out of them. I can remember a friend of mine, I went to school in Nebraska, and I can remember a friend saying this statement, and it's unfortunately almost true. He said, the state tree of western Kansas is a telephone pole, okay? Because you just didn't see anything of any height anywhere out there. It was just all prairie, grasses. Well, there weren't any trees. They didn't have any wood. There weren't that many rocks. How are they going to build their houses? Well, guess what they found? They had to get rid of the prairie grasses anyway. They found that if they spaded them up, those grasses, that root system held the soil really, really well. So they basically went in and pulled up bricks of prairie grass, cut it off right level to the ground, dug up the root system and stuff, and made bricks out of them. Not real bricks, they didn't kill them or anything. They just built their houses with these chunks of prairie sod. Okay? And a friend of mine lived out in western Nebraska, then they called it the Sand Hills area. And her mom lived in what had been an old soddy. And they had put an exterior on it and they put an interior in it. You wouldn't know it was a soddy except looking at the windowsills, they were about that deep. And wow. And sure enough, in between the exterior and the interior was sod. Chunks of sod they had stacked on each other and built the houses that way. They were very well insulated. That sod, didn't allow much air through because they made them really thick. They needed to. It got quite cold out there, and probably quite hot too in the summertime. So they dug up the prairie thing, used some of that for thing, burned it, did whatever, and then they plowed, they cultivated, they planted the grains, they planted the corn, whatever it was, and they had some really good farming years. But then the normal weather pattern set back in, which was much drier than what they had experienced when they first got there. And with that dry, hot summers, the crops failed. And there was no cover of the ground. They had dug up and destroyed the prairie grasses. And if you remember in Oklahoma, when the winds come whipping over the plains, okay, the musical Oklahoma, and they literally do. I mean, they come, because there's nothing there to stop them. There's no hills, there's no trees. The winds get to blowing there, and predominantly, remember the westerlies? The winds come from the west and just blow, and there's nothing to stop them until you get past the Mississippi River, okay? And when that happened, and it's especially dry, right after the nice rainfall time, and no cover for the soil anymore, picked up huge amounts of soil and blew it to the west, to the east. And that, they found silt deposits in Pennsylvania that came from the Dust Bowl in the Midwest. And of course, that was a pretty depressed time too. I think it was shortly before the Depression. And of course, farms were failing, and there wasn't much insurance back then, and families were just having to take up, and they tried moving west to California. If any of you have ever read The Grapes of Wrath, goodness gracious, who's that author? I believe I can't think of his name right now. But anyway, really famous author. Probably won a Pulitzer, maybe even a Nobel. I'm not sure if it's for Grapes of Wrath or some of his others, but it's a really sad time. Say again? John Steinbeck, exactly. Thank you. Okay. You were Googling it?
I Googled it.
Yeah. John Steinbeck. I don't remember, does it say there if he won the Pulitzer or Nobel for it, for literature? Yeah, you don't have to look. I just wondered if it was on the screen. But that was a very sad period in the U.S. history. Okay? That soil that was dropped out of the air, deposited everywhere east of there, that was loess. Fine dust deposited over a very large area. Okay. Now, I told you you would see these again, but we talked about them before with stream development. Now we're talking about landscape development. And you'll see some of the same things. We're not quite there yet, but you'll see them. Let's talk about the landforms. What do we mean by that? These are the Earth's surface features. Okay? In the area where we live, the landforms are folded mountains. Okay, Red Mountain, Shades Crest Mountain, Double Oak Mountain. Those are all pretty much folded mountains. And lots of hills. Okay? In fact, I get a kick when I drive down Bessemer Superhighway right here, drive down toward Birmingham, just not more than a few miles from the college, going north and east. You get up on a hill, and you can see all of Birmingham. I mean, and you're miles away from it, at least 15 miles away. You can see it all. Of course, you get down in the valley, you never see it again. So there's a really big landform there, a hill, okay? The Earth's surface features, okay? Some of these are very broad features, like I mentioned, the mountains, the plains and plateaus. I'm guessing that sort of was a plateau or a very tall hill I was on that I could see all of Birmingham. And basically, when we're driving east on I-20, there's a place many miles from Atlanta. You get up on top of a hill and you can see the whole skyline of Atlanta. And you get back down, you don't see it anymore until you get into Atlanta. Okay, so there are those broad features. The mountains are the tall hills, the plains, the plateaus, whatever. Then there's more minor features, and I would put ridges in here too. That's what you're on in both cases, ridges. Hills, valleys, canyons, those kind of things. They're smaller in area, okay? Now, how are they developed? Well, generally determined by three features. Number one is the rock structure, okay? And I think you've hit this before, but if you haven't, it's a good time to hit it now. Generally, your igneous rocks are enduring rocks, okay? They are slow to erode. They were formed with fire, and they pretty much have really strong structures. Your sedimentary rocks, on the other hand, tend to be a little softer. So if you have much wind or rain or water erosion and stuff, they get eaten away a little bit faster, okay? And metamorphic rock would then be generally as hard or harder than igneous, but certainly harder than sedimentary, okay? So the rock structure is one part of it. Another part is weathering and erosion. What three types of weathering do we have? Say again?
Shall we say wind?
Okay, yeah, okay. Erosion, yeah. Okay, you're hitting the erosion part. Okay, let's hit erosion. We have wind erosion, water erosion, and ice erosion, the glacier. Okay? How about weathering? What three basic classifications do we have of weathering? Earlier in the chapter. Chemical weathering. Before that, mechanical, or also called physical or mechanical.
Is there a wedging?
What?
Wedging.
Wedging is a type of physical or mechanical weathering. And what?
Exfoliation.
That's another type of physical.
Biological.
Biological, okay? The physical or mechanical, you can think of it this way. Physics, chemistry, and biology, okay? Physical weathering, which is mechanical weathering, chemical weathering, and biological weathering, okay? Now, of those three kinds, physical weathering can happen anywhere, anytime, anyway, but your chemical and biological, there are two major components of both of those that contribute to the weather. Temperature and moisture. I think I mentioned that before, and I gave you the rule of thumb also. For both biological and chemical weathering, pretty much 40 degrees Fahrenheit and below, it's kind of at a standstill. It's very, very slow. But for every 10 degrees over 40 degrees, you double the rate of biological and chemical weathering. So your weathering is going to happen more when you have high temperatures and high moisture. Guess what we got? Both, okay? High temperature and high moisture. So therefore, our soils tend to be weathered more so than just about any other part of the country. Southwest, very high temperatures, but very low moisture. So biological and chemical weathering, very slow there. Go up north, generally lower temperatures, though they may have plenty of moisture. Low temperature, it's going to stop, okay? Or be very slow. So, the rock structure contributes from the parent material, the weathering and erosion, that's basically where you live. Now, the third, the stages of erosion. And to me, that should be under erosion, not really a third, but the stages of erosion. I grew up in Georgia, or went to school, most of my schooling in Georgia. And I remember hearing someone talk about, I can't remember which class it was in, but Georgia has a little Grand Canyon. Okay? Have any of you ever seen, I don't even know where it is. Okay? It was totally man-caused. Someone went in and dug up some soil or decided to do a farm or something in an area that just was not suited for it. Once that soil started eroding, there was no stopping it. Okay? So the stages of erosion, the more it's eroded, it tends to be more easily eroded after that. So that's why, that's sort of one reason, one component of that. Okay. So let's look at the three of those. First, the rock structure. Determines the shape of the minor landforms. Okay? You remember right at the end of the last chapter, we had these igneous intrusions into sedimentary rock. Remember, I think that's the last question on your test. Okay? What were some of those names? You remember them? The igneous intrusions into the sedimentary rock. Remember, there's this picture and they had these different forms on it? Features? Okay, it had to do, some of those were basaltic rocks, but they were the batholiths, laccoliths, sills, dikes, hogbacks. Remember that? That last part? Well, everybody's turned it in. Okay. Pretend I didn't say that. No one's listening anyway. Okay. So, but those are examples of minor landforms. Minor landforms that were created by the parent material. Some of that was sedimentary, some of it was igneous. The igneous going to last longer. So these refer to the type of rock. The igneous rock, generally very hard, very resistive of erosion. Metamorphic, they're usually pretty hard and especially resistant to chemical weathering, the second type. Sedimentary rocks, susceptible to chemical weathering and physical weathering, and I would probably say biological weathering as well, okay? I'd say they're susceptible to all types, but especially chemical. So that's the rock structure, how that influences. And we talked about this earlier. I forgot that we were going to have a separate slide on it. Now, some of these rocks have some real attitudes, you know? What do we mean by the attitude of a rock?
The fact that the disturbance by faulting or something.
Oh boy, he reads well. Okay. The attitude of the rock would be the effects of the disturbances that were created by the folding and faulting. When you have folded rock, something's going on in the plates. You got pressures or something, especially compressive pressures in the rock, and probably way down deep, and where it's sort of plastic. And when pressure comes, something gives and it folds the rock up, and that folds the rock above it and stuff like that. The effects of those disturbances by folding or faulting. When you have those, that gives the rock a whole new attitude, okay? In other words, you have these abrupt changes in the features. The folding and faulting can hasten erosion. Sure it can. It makes slopes steeper. The steeper the slope, the faster the water flow down the slope. The more exposure you have, the bigger area for the wind to erode. Yeah, the folding and faulting will change the attitude or the placement or the presentation of the rocks, yes.
Is that how the Devil's Tower got to look like it does?
That's partly, but as you mentioned before, Devil's Tower, if I'm not mistaken, was basaltic rock, right? Didn't y'all, some of you report that? Basaltic rock are good, strong, igneous rock. Probably around that, you had sedimentary rock. That the chemical, physical, maybe even a little biological weathering ate that away. It washed away physically, left the basalt pile standing there. And that's what made Devil's Tower what it is. And more than likely that was something like one of those, which would that have been? Kind of like a stock, just a protrusion of magma rock that cooled quickly, making basaltic rock. Probably that's where it came from. Yeah. More questions? You just.
No,
Okay.
I'm trying to get on artists.
Right, okay. So that's what we mean by the attitude of the rock, how it's placed, and what's exposed, that kind of stuff. Okay, weathering and erosion processes, that was the second one, influenced and controlled by such factors as climate and elevation. Okay, let's talk about the climate. Warm, moist climates. That's where the chemical weathering dominate. And also biological weathering dominates there too. Anywhere you have warm temperatures, moist environment. Chemical, because just about all your chemical reactions were associated with water. They speed up with that rule of thumb. Every 10 degrees they double the rate at which they happen. And biological is pretty much the same way. You got to have warm, moist environment for those microbes and other things to grow. And when they're growing, they weather. Okay? Now, usually in those warm, moist climates, Okay, we're talking about climate and elevation here. The landforms have softer, rounded outlines. If you've ever been in the Appalachians, you'll notice that about it. Appalachians are not jagged in general. They're very rounded mountains. Trying to think, I think one of the main mountains in Great Smokies is Kingman's Dome. I believe that's it. Has anyone been to the Smokies? I believe that's one of the big mountains there. And it's nicely rounded, you know, a very, very lovely mountain and a fun mountain to hike up. I think I haven't done it, but a kid who lived with us took time and went over. He and a friend decided to run up the mountain. Okay, not me. Okay. In the dry climates, however, your mechanical weathering dominates. The winds and I was going to say moving water. You don't have much moving water in the dry climate. It would mostly be wind erosion. There you have sharper, angular outlines are much more common than you have here. Okay, I'm not shaking, am I? Okay. Looked like the board was shaking on this one. Okay.
I think it's perfect.
Yeah, I wonder if it's a mechanical system or something. Is it doing it again?
Yeah, now it's fine.
Is that something upstairs doing it, or is it here? Huh?
There might be people walking up there that are moving.
What's that? You think it's something up here? I couldn't tell if it's that moving or this moving. That was weird. Okay. But anyway, you can sort of tell those. And that has to do with, again, your, as they say here, climate and elevation. Of course, anything that's elevated is going to be more susceptible to the wind erosion because it's up there in the way. And also, the more it's elevated, the steeper the slopes, so the more mechanical weathering you'll have there with the movement of water. Now let's look at the stage of development. And this is the part I was talking about. If you remember what they said about stream development, almost the same thing here with landform development. Describes the cumulative effect of the formative processes. I almost feel like the author got repetitive here, okay? He forgot he had already talked about this. You have the youthful landforms. Here, the weathering and erosion are still in the beginning stages. The mountains have steep peaks, narrow, deep valleys. It's just like what we talked about with stream formation, right? Almost the same words. We did use maturity. Here, the original structures have worn down, and the steep, jagged, sharp peaks are now rounded and not quite as sharp as they were before. Okay? Here we go again. Wow. Okay. The original structure is worn down into rounded peaks and a little bit gentler slopes. Because if you think about what happens with weathering, the sharp edges up top get worn off, so you have soil being formed or gravel or other things. That moves sort of downhill, so your top gets worn off, your valleys get filled in, so your slopes aren't as great as they were before. Okay? So that's moving toward maturity. Then in the old age, I don't like to talk about that too much, okay, characterized by nearly flat rolling plains. The peneplains are the nearly flat surfaces. I think in the last lab, several of you found some peneplains on your topographic maps, didn't you? These areas where you have almost no steepness at all. Okay, very flat surfaces. You may have been finding some peneplains. And I found Emmanuel. Okay. Has anyone else come in since the called roll? I don't think so. I don't think I've missed anybody yet. Okay. Now, occasionally in those peneplains, you'll have monadnocks sticking up. Pretty level areas and something will be there. Okay? These would be hills, and again, think back about the things that contribute to these features. This may be very resistant rock, like maybe an igneous rock under, surrounded by sedimentary rock. Sedimentary rock have worn away, igneous rocks hanging on for dear life. Possibly metamorphic, more likely igneous, okay? That could be part of it. Another part of it is that Carl's here, okay? Okay, anyone else come in since I called it off? Okay. And I see this, say, on the farm over in Georgia, okay? The field where we built our house is only used as a pasture because it's just too rolling. Why is that field hilly and rolling like that when the one next door to it is a lot flatter? Well, in this hill, boy, the guys who were digging out the foundation for the house, they found out really fast. It is one heavy, hard, resistive clay. So it's not just resistive rock. Sometimes the hills will be resistive soils. And the clay on that hill is hard to move. We were planting posts in it. Not a pleasant experience there either, And the old guy who was working the bulldozer trying to dig out the foundations, I mean, it was beating him to death. He actually, and he did it in August when it was very dry and hard and hot. And he literally, we were in fear he almost had a heat stroke that day. We weren't there to see it, but my brother said when he drove by and saw him, he said he was red in the face and he never was. I mean, it broke him almost physically. He was too old to be doing that anyway, but he loved that bulldozer. But it beat him to death. I mean, it really did. So not only hills of resistant rock, you can have real hills of resistant clays or soil structures. It's really hard to penetrate. Now, these are youthful, they're going to maturity, going to old age, but the thing doesn't stop there. You get rejuvenation. This is when the land is uplifted, and then the erosion processes begin again. What creates that uplift? The plate tectonics, generally, or things like that, which create new folding, new faulting, maybe even volcanic activity, something that makes new, and nothing ever stays the same. Okay? It's very slow change, but it's always changing. Okay? That, folks, is the last slide in chapter 20. Now, before we move on out of 20, trying to get over here where I have a little bit of light, there is a really nice blurb on the top half of page 515 in my book, maybe a different page number in yours, and this is Science and Society, and it's talking mostly about acid rain. And I think we've mentioned that before, all the events that occur that create rain or moisture coming from the sky that is a tad on the acid side. Every time you have lightning, you have nitrogen oxidizing to form nitrous oxides. You mix that with water, you get some type of nitric acid. Maybe not really strong, but some type of acid. You get pollution into the air with sulfur dioxide in it. Get rain, you have sulfuric acid. Okay? Carbon dioxide in the air, mixed with rain, you get carbonic acid. Just about everything turns into slight, mild acids. So just about all your rainfalls is slightly acid. So this does wear away soils. Nice little blurb here, well worth your effort, and that has questions to think about. Take a look at that. I should have mentioned that back earlier. There is in the section on people behind the science, there's a John Wesley Powell mentioned here. Rough-looking old dude here, but they call him one of the most romantic figures in the 19th century U.S. geology. I always think of romantic figures in U.S. geology. I mean, that's the first thing that comes to mind. No, not really. Okay. But he was sort of he was an interesting old character, okay? If you read through this, you'll probably see a few other names or things talked about. Grove Carl Gilbert, Clarence E. Dutton, W.H. Holmes. You'll see several others mentioned here. Any of those could be potential paper topics, okay? And just some of the features of the geology and things that he studied as well, okay? There's several really nice pictures that weren't shown on the slides. And then we get to the end of the chapter. You know what's coming, don't you? Nothing replaces reading the chapters, okay? Nothing. The slide sets, the YouTube videos, nothing replaces reading the chapters. Please read it. If you haven't already, you get the most out of it if you read it before I talk about it. But even then, if you don't read it then, read it afterwards. You'll pick up and tie things together. Then there's a summary. And the summary for this chapter is sort of like the last one. Pretty short. So that can't be your major thing to study, though it has got important stuff in it. Key terms, one of the shortest that I can remember seeing. Key terms, okay? Applying the concepts. Multiple choice questions, and there's 45 of them. That's a bit, probably a little below average, but right near average. With answers, if you can work through those, you have a really good shot of, that's a great study tool for the chapter test. Questions for thought, there's 18 of them. That's about normal, I think. For further analysis, only 3. I believe that's a little on the low side. And then you have the parallel exercises. We didn't do many of the things like that, but you might want to look at some of those. If you have the big books, the answers for the group A's are in the back, not for group B's. If you have the little thin books, none of the answers are in the back. Okay. Any questions? Chapter 20. Now, last time we did the lab that goes with this chapter. It really doesn't go that closely, but the one that we did with the chapter. This next chapter, if you got a big book, well worth a look. If you don't have the big book, it's not even there, okay? But it's geologic time. You will not be tested on it or anything else. But if you got the book, you might want to take a look, read through it. It's up to you, okay? Good stuff there, though. We just don't have time for it, for geologic time. But anything you see there, here's Edward Seuss, who is People Behind the Science. He would be a legitimate, he was an Austrian geologist. So you can use him as a paper topic. Several things are mentioned. Now, I really wish we had time for chapter 22, because that feeds into chapter 23. But we don't have time for both. And I thought weather and climate, since that's one of the main features in your course description that's mentioned, we didn't have time to do atmosphere of the earth, but we did have time for weather. So if you have one of the bigger books, this is even a more important chapter to sort of scan through, because we're going to be talking about some of the terms that are here. I will go back and fill in the gaps or anything you may be missing, but it's well worth a look if you've got it, okay? And again, anything you see there is a potential paper topic. Lots of stuff, good stuff there. It's a long chapter. That's one reason we can't do it. It's really long. People Behind the Science are, James Ephraim Lovelock, and they indicate he may still be living, but funny they don't have a picture of him that I can see anywhere. Maybe up in the... No, I don't think so. So that's another potential for you there. Okay, but you're not responsible for either 21 or 22. So we're moving to 23. So let me end this. Any questions on 21st? 20 before I move? Okay? then let's close this out and move on to,
Removing desk, that's what's doing.
what's that?
Removing desk upstairs, that's what's done.
Yeah, that's what's doing it. That's what I was wondering. It's either shaking this or shaking that, or maybe both. I don't know what they're doing upstairs. Maybe they're stripping floors or moving desks. I don't know, but it's bizarre. All right, let's move on to 23. Weather and climate. Now, in some of our other chapters, we had compound names like rocks and minerals. We actually did the minerals first and then did the rocks. This one, however, we will do it in this order, weather and then climate. Okay? So let's start from the beginning, weather and climate. By the way, we will not have a paper lab for this chapter. Okay? The lab for this chapter will be the visit to Channel 13 Weather Center, if I can arrange it. Like I said before, not everybody was in here then. Jerry Tracy, the Tracys go to our church, so I know them. They're really nice people. So he's the one I've always contacted. He's always glad to have us. But this is springtime, and who knows what the weather's going to do. If they have a bad weather day on the day we are trying to go, we're not going. Not just because we don't want to be driving in bad weather. He's going to be up to his ears in following stuff and reporting and stuff, and he wouldn't have any time for us anyway. To me, it'd be fun to watch all the activity going on there, as long as we don't bother him. But when you get there, you'll see it's a very small space. It's going to be hardly any way we wouldn't be bothering. And that's happened before. We lined it up, and then bad weather struck that day, and he called and said, "Look, I can't handle you this day. We're going to be," or we had bad weather the day before, and he was up all night having broadcasts. So not going to happen. So we'll see. And before Richard Jackson's help, he moved on to something else. I think he's selling real estate. Stephanie Walker has helped us once before, and Harmony Mendoza just a little bit, but not much. Do they have anyone else at Channel 13 anymore? I don't know if they have brought in anyone new to replace Richard. I don't know. So anyway, it's all up to them whether we have a lab on this chapter or not. But that'll be at the end. Let's get started now. The core concept here, and again, I say this just about every chapter too. In my book, it's on page 567, and they put it white print on a yellow background, which is really hard to read. This is much easier to read, and I think it's verbatim here. Yeah. Solar radiation drives the cycles in Earth's atmosphere, and some of these cycles determine weather and climate. That's definitely true, but there's some other things that drive as well, and like I said, I regret. I was tutoring a student right before class, so I didn't get set up. I didn't get set up quite the way I wanted to, so now we'll catch up a little bit. I say every time, I should just bring this in every class, because I'll think, oh, we're not going to need that this time, and then sure, we need it again. Does anyone know which way the world turns? Not the, yeah, looking from the top, yeah, counterclockwise. You're looking from the bottom, that happens to be clockwise, yeah, but from the North Pole, it's counterclockwise. Why do we know that? Because the sun rises in the east and sets in the west, okay? It's a dead giveaway. It turns that way. All right. It says solar radiation drives the cycles in the Earth's atmosphere. It does, okay? But other things drive it as well. For instance, the spinning of the Earth. And this is some part, I think probably the previous chapter would have talked about, but we're not doing that chapter. Because the Earth is spinning like this, Okay? Now the Earth is solid liquid, right? Okay? Mostly solid, but has liquid components in it. It all goes pretty much together. The atmosphere, though, is gaseous around here. It doesn't have to do just like the rest of the Earth. It's a fluid. It doesn't have to, okay? And if you think about it, when the Earth's spinning like this, the air, its inertia tries to keep it pretty much where it was. So near the equator, you have mostly easterly winds because they're standing still and the Earth's turning underneath them. It feels like the wind's blowing, but in reality, the Earth's moving under it. Okay? Does that make sense? And they call those the trade winds because back in the sailing days, the wind, you got into those areas and the wind just moved you right along. So they almost always tried to go east to west if they were near the equator. Okay. Now, because the atmosphere around the Earth here, the Earth is spinning under it, the Earth does drag it some, okay? Pulls on it some. So it starts the atmosphere moving this way, but it's not as fast as the Earth's moving. But you see, here, the Earth is moving very fast relative to the atmosphere. Here it's not moving nearly as fast because it doesn't go as far around. So actually you get the winds moving this way, and then up in the temperate regions, they curl around, and that's why we have prevailing westerlies. Because the equator, the equatorial belt, has yanked the atmosphere around, got the atmosphere moving this way, but then up here, the atmosphere is moving, but it's moving faster than we are. So that's why you have prevailing westerlies up here. So it's not all solar radiation. Yeah, what solar radiation does, it heats around here and causes convection moving upward, and then you have cooler air coming down, and that forms your hurricanes, weather systems, tornadoes, all those kinds of things. That's the solar radiation. That drives cycles in the Earth's atmosphere, but other parts is because of the spinning of the Earth. So I wanted to mention both of those. Some of these cycles determine or at least influence weather and climate. Okay? Now, anyone want to hazard a guess of what that's a picture of? Anyone see?
A picture of a storm from outer space.
Okay, storms, you say?
Yeah.
Okay. Can you tell where it is? This is the state of Florida right here. There's the Keys, This is Georgia. There's.
Oh, yeah.
Yeah, you see it? There's Louisiana.
Yeah.
There's Texas. Okay? This is the Gulf of Mexico. And guess what? Gulf of Mexico, one hot, warm bathtub, right? Always evaporating water, getting moisture into the atmosphere. Look at all that cloud cover down there. Is that the storm you were talking about? I don't know if it is a storm, but I bet you they're getting some rain out of that one. Okay? It looks like there could be things happening up here. I don't know if that's landforms or if that's cloud. But yeah, lots of things are going on here. Okay? And solar radiation is creating the moisture or making the water evaporate. So sure enough, solar radiation is important there. It's warming it, and you get the high pressure, low pressure areas. All that stuff is happening. And solar radiation is a major player there. Major player. So, we're going to start, and the first half of the chapter is weather. They don't list it that way, but it is. The second half is climate, and it's not quite half, more weather than climate. But let's start with clouds and precipitation. And that's certainly influenced by the solar radiation. Okay? In so many of our chapters, we have cycles going. Rock cycle, uniformity, diastropism, everything goes in cycles in science, pretty much. The good old sinusoidal curve, the periodic happenings. So we're going to talk about the hydrologic cycle here. Okay? Let's get the illustration up here. Let's start with the ocean. Most of the surface of the globe covered with water. Huge amounts of water. We'll talk about that in the next chapter. Okay? Huge amounts, expanses of water. Much of this water in very warm areas. Look at the Pacific here. Wow! In the tropics, huge area of water. You go across a little bit of land, then you got the Atlantic. Go across a little bit more land, you got the Indian Ocean. Okay? Then you're back in the Pacific again. Huge areas of water. Okay? That solar radiation coming down, heating the water, warming the water, and getting Darius into class. Okay. Got it. Has anyone else come in since I called roll? Okay. Didn't see anyone. So that's where we'll begin anyway. All this water and the sun hitting it, causing evaporation. Water goes up into the atmosphere. Now, somewhere in the atmosphere, and if you had studied the chapter before, which we haven't, it's not in most of your books, but if you do have the bigger books, you can go back and read, you have temperature gradients as you go up in the atmosphere. It gets quite cold really far up in the atmosphere. Incredibly cold. Have any ever made any major jet flights before? Okay, some of you have. Did you have the opportunity to look at the screen and see what the outside temperatures were? Oh boy, really? Yes, you don't want to open the windows, right? Okay. For many reasons. Okay. They won't let you is one. Okay. Okay. Very, very cold there. So this warm, moist air goes up into the atmosphere, and at some place it hits some pretty cold layers. So some of that that water that evaporated here now starts forming little droplets here, forming your clouds. Okay? We saw those over the Gulf of Mexico. Now, most of the time, either prevailing easterly winds near the equator or prevailing westerly winds in the temperate areas, they are going to blow the clouds either to the east or the west. For our sakes, let's talk about blowing to the west. So here's the Pacific Ocean out there. Evaporation goes up, clouds go up. Either the spinning of the earth or the winds from the earth, whichever, the clouds move and go over a landmass. Now, the answer to this depends on the time of year. But do you think the temperatures of land masses and water masses are about the same? Generally not. Okay? Usually in the wintertime, the water's warmer than the land mass, and in the summertime, the water's cooler than the land mass. It's just water has a very, very, very high specific heat, which means it tries to equilibrate and keep it closer to the same temperature all the time. Land mass has very low specific heat. It heats and cools like crazy. I think you probably realize this if you've been to the beach, Gulf Shores or somewhere down there in the summertime. You're driving south, it's already summertime, it's pretty hot, and you drive south and it just seems to get hotter most of the time, right? You get down to Montgomery, it's usually a few degrees hotter than it is here in Birmingham. Keep going on down, it may get hotter, but then suddenly you pass somewhere down there and you start getting the breezes off the Gulf and it actually feels cooler. Maybe very humid, but it actually feels cool. You get on the beach, it actually does feel cool. Why? Because the water has a higher specific heat than the landmass. So you may be 10 degrees cooler on the beach than you are 10 miles further north because you're over landmass there. But in a lot of time of the year, you're going to hit cooler area here. When you hit the cool area, now the precipitation, that's not me, okay, that got it into the clouds, they get so heavy, it falls out, okay? So you have transport through the atmosphere, that's this part. Then you have condensation. Now what does condensation mean? Evaporation is going from liquid to gas. Condensation is going from gas to liquid, exactly. So you have condensation happening, and when those droplets condense enough, and collide and, get big enough, then they drop out of the air. That's what we mean by precipitation. That means falling down, going down a precipice, you might say. Okay? In chemistry, you have precipitation. A solid comes out of a liquid. That's precipitation. Something falling down, that's what we're talking about. Well, what happens? It falls onto the land, or it falls into the ocean. It could. I have storms in the ocean too. But if it falls on the land does absorb some. Hopefully it absorbs a lot. But others runs off, and where does it wind up? Back in the ocean again. That completes the cycle. Everything goes through cycles. Now, returns to the ocean. Now, there's many smaller subcycles. Like these clouds here may move just a few miles, and then the temperature drops or something and hit a front or something, and then falls right back into the ocean. That's a real short circuit there. Over here, it could precipitate over land and maybe go into a lake and re-evaporate and get into a little subcycle there. Okay? So yeah, you can have all sorts of minor cycles, subcycles, but the big cycle is that we just described. Make sense? All right. Let's look at that first stage there, the cloud forming processes. Now, here in the southeast, we're usually used to talk about humidity, right? A lot of times people say, that's a lot worse than heat is the humidity. Well, they go really together pretty much. What do we mean by humidity anyway? And the actual word is relative humidity. It's the moisture in the air. And why do they put relative? Does that mean first cousin or something like that?
Always moisture in the air to some extent.
What's that?
There's always moisture in the air to some extent.
Yeah, there generally is. And most of the time we have relative humidities in the, I'm just guessing, 50, 60, 80, 90%. Very rarely will we get down into 20 and 30%. But it can happen. The bad drought we had this past year, I bet you there were many days we were down around 20 or 30%. Pretty dry for our area. You get out west in the deserts, if they exceed 10%, they count a humid day, okay? Very, very different there, okay? So basically, while they say relative humidity, what that is how much moisture is in the air compared with how much the air can hold, or the ratio of what's in the air compared to what it can hold. Now, what kind of air holds more moisture? Warm air or cool air? Say again? Cold air holds less moisture, okay? Picture the glass of iced tea you pour in the summertime. You set it on the counter to go get your bag of chips. You come back, and what's outside that ice? We call it sweating. What's happening? The moisture right next to that iced tea glass, the air right around there has now suddenly dropped in temperature because the glass has ice in it. So it's cooled the air, and now the moisture comes out, okay? Because it's the same amount of moisture in the air out here as there, but the cool air can't support as much. So the relative humidity just shot up, even though the amount of moisture in the air actually went down, okay? Because it can't hold as much. So clouds form when the air masses are cooled to their dew point. The dew point is when you reach that point where it can't hold anymore. So either you're adding more moisture to the air until it can't hold anymore, you reach the dew point. Or you have all that moisture in the air and you drop the temperature until you get to a temperature you can't hold any more moisture in the air. You haven't added any moisture, you drop the temperature. Either one of those gets you down to the dew point. So that's what's happening. The clouds form when the air masses have picked up moisture, like over the ocean, picked up lots of moisture, but risen in the atmosphere until they cool to the point they can't hold any more moisture, then they start dropping out. generally cooled by this upward movement. And what is that upward movement called? Convection. That's when warm air rises and the cool air comes underneath. You get this. The other thing that causes the cooling is, remember back here, the warm, moist air coming off the Pacific, say, comes in, and what's just inside the west coast of the U.S.? Mountain range. I mean, Seattle's right on the ocean. Mount Rainier is just right inside of Seattle. And on the west coast, it's like that. On the east coast, flat forever. Or for a long way, you don't have that going on. But on the west coast, you have it going on big time. In fact, Seattle, Washington, one of the wettest places in the U.S., right? You cross the presidential range, and you get into eastern Washington, extraordinarily dry. Almost to the point, it's not quite a desert, but very dry. Because the mountains, the warm, moist air hits the cool mountains. You know, they go up in elevation, your temperature drops, then the moisture falls out there. So the barrier mountain ranges, okay? That is where the moisture, that stops it. That cools it. And the third one is by colliding air masses with different densities. Now, why do they talk about air masses with different densities? What creates a density change in an air mass? Temperature, heat and temperature, exactly. Okay? Because which is denser, warm air or cool air?
Warm air?
No, warm air is less dense because the molecules move further apart because they're moving faster. You heat something up, it moves faster. And that's why over the eye, the water goes up, and around the edge of the pot, it goes down. Okay? The warmer fluids, whether it's liquids or gases, they expand when they heat and they contract when they're cooled. Okay? So that's colliding air mass with different density. A cool air mass comes in with high density, a warm air mass with lower density. They're going to undercut each other. Okay? That may be the cooling by the colliding air masses. Now, the cloud formation depends on the atmospheric stability. I don't know if you listen to Jerry Tracy or James Spann or some of the other weathermen, but have you ever heard them say unstable air? Y'all don't listen to the weather ducks, do you?
I've heard it once or twice.
What's that?
I've heard it once or twice.
Yeah, and if you listen carefully, you'll find them saying, if you're going to have a storm, they're going to start about the unstable air most of the time. What do we mean by that cloud formation? Now, it seems like to me I want to make sure I'm not going to skip over something here. Okay, no, we're not there yet. I want to make sure I didn't skip over something I thought we were losing. Let's look at atmospheric stability. Now, actually, Jerry Tracy likes to give this illustration when we do get to go there. I think this is how he says it. His children are grown now, but back when they were little, he could lift his son or his daughter up over his head if he wanted to. Not too much problem, right? That was a sort of stable situation. But then I think he's used this one before. What if he tried to lift Arnold Schwarzenegger over his head? That would not be very stable at all, okay? If you have the denser part up and the less dense on the bottom, you've got a problem, Houston, okay? So here's what a stable atmosphere is. Generally what happens, you have warmer air rising. So if this lifted parcel of air is cooler and denser than the surrounding air, then it wants to go down and the warmer air go up. If that's happening, that's a very stable situation. If the I don't like the way they've worded it here, but that's basically saying if the listed parcel returns to the original level, if it's denser, it goes down, the warmer air goes up. That's pretty stable. Okay. The unstable situation, if the lifted air is warmer, and this is backwards, no, that's right, and less dense than the surrounding air, then it's moved to a higher level, and it'll continue to rise, and when that happens, you start having these currents, and if it's really big currents of warm, moist air rising real quickly through cooler, denser air, and when you have the movement upward, I don't know if you remember this from the earlier chapter, because the earth is always spinning, and you have movement upward, you get twisting action. It's called a torque, and that then is what creates thunderstorms, tornadoes, or really big scale hurricanes. And you have and that's your unstable situation. These are called thermals, the uplift of the warm, moist air. Okay? Now, this diagram doesn't do a whole lot for me, but it is showing it right. Okay? So here you have a parcel of air. It's on its way up. The temperature, the parcel of air is cooler than the surrounding air. So here's the temperature of the surrounding air. This parcel of air is cooler than the air over here. It's happy where it is. Okay? Its rising is like this. That's cooler than the surrounding air. So it's just going to move right up that gradient. Surrounding air here, no problem. Stable situation. Generally not going to have much storm in that situation. Okay? However, if your rising parcel of air has a warmer than the surrounding air, then it's going to tend to keep rising. Okay? Let's go back to this one. Notice it's going to tend to go down. Well, it's already on the downside, and it just continues. It reaches its equilibrium and is happy. This one, however, since it's warmer, less dense, it wants to just keep rising. But when it does, and lots of this is happening, you start getting a lot of movement upward. Warm, moist air moving up, maybe getting some twisting action from the Coriolis effect, and cooling as it goes, you can have a storm. Big thunderstorm, little thunderstorm, tornadoes, hurricanes, whatever. If you have this going on, this is going to be an unstable situation. And that would be creating those thermal convective currents. Okay? Now, I don't know if y'all are listening. Y'all are here most of the time, so you probably aren't listening to the thing. I worry about walking so far from my computer, but here I'm in the middle of it, so it's over there, it's plugged there, but I have to talk here. I don't know if my voice is projecting well. Has anyone had any trouble hearing me if you've listened to any of these things? So far not. Hopefully it's picking up okay. The old program we had, Integrity, it showed the motion of the sound, a little indicator showing how well it's picking up. I don't have one on this, so I don't know. Okay, so what happens? The rising moist air cools, eventually reaches the dew point. Remember, the dew point is the point of temperature and moisture where it can't hold any more moisture. And that can be caused by increasing the moisture or dropping the temperature, usually dropping the temperature. But, y'all know this too, don't you? When you go in and y'all are young enough, you probably take these long hot showers, right? And the whole room steams up. You've reached the dew point, okay? The air is so thick in there, okay? It can't hold any more moisture, okay? But you open the door to the bedroom or hall or whatever your bathroom opens into, and that dry air comes in and everything just dries up almost immediately because it can hold the moisture, okay? So, the rising moist air cools, eventually reaches its dew point. The droplets condense around these things called condensation nuclei. in the saturated air. Now, if you don't have these condensation nuclei, we'll talk about those in a minute, actually the air can become supersaturated. And then any influx of something, you can really have some major storms going on then. Especially if the air is moving up rapidly, ooh, it could be bad. So what are these condensation nuclei? They mention a few in the text. That's what I was wanting to make sure we covered. I was afraid we were missing it. This is in my book on page 571. I think it's where I saw it. Okay. Yeah, here we go. Condensation nuclei come in different sizes. Okay, let me back up one line. It would appear difficult for cloud droplets to merge or coalesce with one another since the air movement moves them all in the same time, not bringing them together. The condensation nuclei come in different sizes, however, and cloud droplets of many different sizes form on these different sized nuclei. The larger cloud droplets are slowed by less air friction as they drift downward, and blah, blah, they go on. So that paragraph, well worth a read, okay? In fact, the whole section is well worth a read. The whole chapter is well worth a read, okay? So those are the nuclei. Let me mention a few things. I thought we were going to say it somewhere else in the book. Some places these could be little salt particles. Remember, a lot of this came out of the ocean, and maybe some salt particles actually made it up. Most of the time, the salts stay, and only the water evaporates. But it's really hot, or if you have wind blowing over it, you have little droplets, and salt makes it in there too. Those little salt crystals could be condensation nuclei. Little ice crystals could be condensation nuclei. Dust particles could be condensation nuclei. We got plenty of that, don't we? So just about anything could be those condensation nuclei. Now you want it to be something that absorbs water as opposed to repelling water. And by the way, there are a couple of terms you might run into sometime in the future. One of these terms is, it's a pair of terms. Things can be hydrophobic or hydrophilic. What does that mean?
Hydrophobic is fear of water.
Fear of water, and hydrophilic, philos, is love, the love of water. Okay? So for instance, oil would be hydrophobic, but there's a crystal called magnesium chloride, I believe it is hydrophilic. It loves to attract water. I would say your table salt is hydrophilic, isn't it? In the summertime when it's real moist, take that salt shaker and it's just lumps of things because it's absorbed water. A lot of people put rice in there to absorb the water away and let the salt come out. Okay, any of those things could be condensation nuclei. Okay, so the rising air is cooling as it's going up. The cooling is slowed by the release. Okay, now here's another thing. When I add heat to something, what usually happens?
Expands.
It what? It expands. How about temperature-wise? It gets hotter. Goes up in temperature. Always?
No.
No. There are 2 points that it doesn't. Okay? This is when it's changing phase. And something is going from, and by the way, you probably experienced this before too. Have you ever washed your hands and maybe, unfortunately, left a little bit of moisture on them and reached into the freezer to get an ice cube or something to put in your teeth, and then cannot get that ice cube off your finger? Ever happen? Or when you do, it hurts. Okay?
Is it the same thing as when you stick your tongue to a hole outside?
Okay, I was wondering who watched that movie. Okay. Did anyone see that? What is it, Christmas Story? Is that the one you were thinking of?
Oh, I just hear people make that analogy all the time.
Right,
So,
exactly. And what it is, if something is colder than the freezing point, you can heat it up and it just increases temperature. But when it reaches the melting or freezing point, you heat it up, then it begins to melt without changing temperature. So you're adding heat but not changing temperature, then you're dealing with what they call latent heat, or the heat that's hidden. Latent means hidden. Okay? Now, the story you're talking about, or the situation you're talking about, if it's way below freezing outside, and stick your tongue to a metal pole, it's going to stick to the metal pole because it freezes the water on your tongue. Now, my wife was the oldest of 3 kids. Her brother was 4 years younger than her, so she had as little to do with him as she could growing up. He was just this painful little brother, you know. But then her sister was just 2 years younger than Keith. Keith, though, is Mr. Cool. I mean, he's tall, dark, handsome, athletic, good, obnoxious. I mean, just like, wow. But he was a kid. The mom had taken he and Terry into the store and was rushing around trying to get her stuff, and they were roaming around where they probably shouldn't have been. And her mother, Mrs. Brazil, was getting ready to check out and said, "Terry, where's Keith?" She said, "I don't know. I saw him somewhere back there." She said, "Well, go find him. Hurry. I'm ready to check out." So she went back, and there was Keith over the cooler down there. And she said, "Keith, what are you doing?" Mom said, "Come on, let's go." He said, Here. It was summertime, really warm. You know. She said, "What? What are you saying?" "Go to that bar." "What?" "Go to that bar." What he had done, the cooler there had this big coat of frost on it, and he was so hot, he thought that looks like that'd be really cool to lick. And he did try to lick it, but it was colder than freezing, so when he got the moisture of his tongue against the thing, it stuck. So he was there, his tongue stuck to the ice in the cooler. And Terry ran to go get her mom and their mom. She came back and she was horrified that her son would put his dirty mouth where everybody's getting their food, you know. So she didn't wait for anything else. She yanked him by the collar and went yank, leaving most of the skin of his tongue still frozen to the ice there, bleeding like crazy. Got him out of the store, stuffed a Kleenex in his mouth so it would be shown. Got him out of the store as much as possible. She was horrified. We love that story on Cool Keith, you know. We tell his kids, you know. No. Yes. Were you going to say something?
Speech impediment or anything from it?
What's that?
Is there a speech impediment or anything from it?
No, I don't think so. He just was in pain for a while until his tongue grew back some skin. Okay. So anyway, that's latent heat. Heat that when you add heat, it doesn't change temperature. It happens at the freezing or melting point. It also happens at the evaporation condensation point. Those 2 points when you change phase from liquid to solid, solid to gas, gas to liquid. There is solid to gas, that's sublimation. But those are the places where you have latent heat. The cooling of the rising air is slowed by the release of the latent heat of vaporization, because when it stops vaporizing and starts condensing, it's releasing heat then. And that's why it slows up. Huge numbers of droplets appear in the clouds. And that's why we see the clouds. There's just lots of tiny little droplets there. Now, what's the difference in a dark cloud and a white cloud? Say again?
Dark cloud makes lightning.
Okay. What it is, the dark clouds, the droplets are closer together, and you're underneath the cloud. They've shaded the sun, you don't see it. If you were looking above them, they'd be white clouds. The white clouds that you look out and see, you're seeing the sun reflecting off of. They have the same clouds. It's just where you're located, whether you're in the shade of the cloud or but the more droplets you have, then the more they darken or shade. And you're about to have a storm. So yeah, you could have lightning too. Okay. So what's the origin of precipitation? Precipitation, I mentioned this earlier, is falling. That's what it means. Precipice, to fall, to go down. Whether it's chemical precipitation of a solid coming out of solution, that's precipitation. Or this, water returning to the Earth's surface. Would that mean dew or frost? Are they precipitation or not?
I think they both are.
Actually not, because they're a surface phenomenon. Moist air near the surface, as the temperature drops, it comes out of the gaseous phase and the liquid phase, and that forms dew. You have those in the spring, summer, and that kind of year. Actually, this morning was one of the few mornings, not the only morning, one of the few mornings where I've had frost on the window, okay? And that's when the moisture in the air dropped and it got close to freezing. I didn't know it got that close to freezing last night, but my car was facing north, and it must have been cold enough because I had a little bit of frost on the window this morning. Not much, okay? And those are surface phenomena, not precipitation. Precipitation must be falling from above. So would hail be a precipitation? Yea or nay? Snow? Rain? Dew? No. Dew is not. Dew is a surface phenomenon. And frost? Not. That's a surface phenomenon. That's surface moisture in the air hitting a cold surface and changing to ice or changing the liquid for dew changing. It's a surface process, not precipitation. So snow, hail, rain, that would be precipitation. Dew and frost, not precipitation. So how does precipitation form? Okay, two ways. We talked about the clouds. They contain, oodles of little droplets of water, but very tiny droplets of water, not heavy enough to fall yet. That's what gives them the whitish or the blackish color. All those droplets are blocking or reflecting light. That depends, okay. But if the dew point continues to get approached, or maybe reached or even exceeded, then suddenly the droplets coalesce. There's so many of them, and they're so close to each other, they bump into each other, and then they get bigger. At some point, they're heavy enough, they're going to fall. So that's one way, coalescence of the cloud droplets. Or the second is, and this happens especially in those thunderstorms in the spring and summer, okay, when you have the really tall cumulus clouds with the anvil-type top, those big, stormy-looking clouds. What's happened, they really are way, way, way up there. So the moisture up there has actually changed to ice. And ice then starts drifting down through those more cloud, because they're way up there, and the moisture in there is attractive because ice is hydrophobic. It is water, okay? So it likes to attract more water. So the ice crystals get bigger and bigger, and then as they get bigger, they get heavier, and they start falling. Now, believe it or not, most of those big, heavy droplets on those summer rainstorms, we talked about that before, come splashing on your window almost enough to scare you. That started as a big hailstorm somewhere up there, just that the surface water temperature was so warm it melted on the way down. But they started as ice crystals. In the middle of summer, they started as ice crystals. And sometimes those rain droplets can be pretty chilly, Of course, the outside air is warm and they feel pretty cold, but most of those did start with that. It's those gentle little showers, not that big a drops of rain. Those could have been coalescent cloud droplets. So this coalescence process, it takes that warm cumulus clouds near the tropics, okay, the tropic oceans. We have a lot of tropic oceans, remember? The tropics are this band, what's the band of the tropics? Between where and where? The what? Tropic of Cancer on the north, or the Tropic of Capricorn on the south, and where are they?
On
What's your magic number? Oh, say again? 23.5 degrees north, 23.5 degrees south. It's a pretty big band there. See these dotted lines? That's it. Look at how much ocean is in between that. Okay? And even most of the Indian Ocean in between that. And big, broad amounts of the Pacific. Oh, look how much Pacific Ocean is there. So yeah, these take place, the coalescent process in the warm cumulus clouds near the tropic oceans. Because guess what? You have to go way up there to get any ice crystals there. Most of the time they're going to coalesce. The droplets will coalesce there. The clouds contain giant salt crystals. Those are your condensation nuclei. I knew we were going to have a slide to that somewhere. Salt, they say giant. They're not that big. But, little crystals of salt. These are hydrophobic. They attract moisture, and those fall out there. So those are usually your tropical rains. And I can remember the first ship I caught for my full-time duty station. I've been on midshipman cruises in the Navy. They flew me to Guam to catch the ship coming off of the Westpac deployment. And I got there several days before the ship did. So I was stuck in the middle of the island of Guam. Pretty island, but no transportation. I was going to have to pay big bucks, and I was in, so I didn't have big bucks. So I just basically, I didn't have much to do. I hadn't started the job yet, so I didn't know what to do. I couldn't get. So I walked every day, pretty much. And usually would take off after breakfast and walk in the morning, come in, eat lunch, and go walk to a different direction at night. And I swear, just about every morning, if it didn't rain every day on the island of Guam, it's because it rained twice that day on the island of Guam. I mean, it seemed like it always, as that rain, it would just come up all of a sudden, no thunder, no warning or anything, just the water start falling. That was this warm, tropic, showers just start raining on it. And I turn around and start heading back to the BOQ, and on the way it would stop, and by the time I got back, I was dry again because it was so hot, it dried me right off. It was just sort of a frustrating experience, but it was a pretty area. So, now, the second of these, the ice crystal process, that takes place at the middle latitudes. Where do we live? Middle latitudes. That's basically between the Tropic of Cancer and the Arctic Circle. That's a pretty wide range there. Arctic Circle is 23.5 degrees from 90, which would be 66.5 degrees north. So from 23.5 degrees, 66.5, plenty of regions there. You get closer to this, it's more Arctic. The closer to that, it gets a little subtropical. But the ice crystal process takes place mostly there. That's where we live. Most of our rainfall is going to come out of ice crystals, believe it or not. The ice crystals capture the nearby water molecules. They grow until they're heavy enough to fall. As they fall, they melt, so you don't find the ice. Unless, of course, there was such an upsurge of warm, moist air going way, way up there, and the upward surge keeps them, you've seen that, the vacuum cleaner hose, put it the other direction, okay, so it's blowing air out, and you can put a tennis ball up there, or a ping pong ball, and keep it afloat. Even though the ball is denser than the air, it should fall, but it doesn't because of the flow of air, right? The pressure of the air. Okay, Terry's here. So far we're only missing Kenesha, Carrie, and James. Is that right? Oh no, Coco. Missing Coco. Okay. All right. So you have these ice, but you have so much air moving up because of your thermals, okay? The condensation, so much air is moving up, it keeps the ice crystals up there, and they keep growing and growing until finally they're heavy enough to fall, and they don't have time to melt all the way. What do we call that? Hail. And those happen in those really supercell thunderstorms where you have lots of that upflow of warm, moist air. Okay? So ice crystal capture the nearby water molecules, keep growing. Now, in the wintertime, north of here, occasionally here, but they fall as snow in the winter. But most of the time down here, they melt on their way down, and they're always right. Okay? If you have the conditions just right, see, most of the time, and you'll hear this in the South a lot, oh, it's too cold to snow. Okay? That sounds contradictory, but if it's so cold, then you don't have any precipitation. Up north, it stays real cold, you get moisture in there, it's going to fall as snow. Here, when the moisture comes in, usually it's from the Gulf, it warms it up, and then it falls as rain. Okay, so, but occasionally we will have the snow. So sometimes those ice crystals fall as snow. Sometimes, most of the time down here, they melt. In the fall, winter, spring, or summer, they melt and fall as rain. But occasionally we will get the snow. But if they keep getting blown up, then they become bigger and bigger balls of ice, and that's when you get hail. Okay. And that's always in the summer, by the way, right? When you have those big updrafts. All right, what are our weather producers? And by the way, let me keep turning the pages here. A real pretty picture on page 571 or somewhere thereabouts. We're at the bottom of 571, getting ready to move into 572. What are our weather producers? Now, here again is an idealized model. This isn't exact, but this is the ideal. The region between 10 degrees north and 10 degrees south, that's really close to the equator. It receives more direct solar radiation than anywhere else, more direct solar energy than anywhere else. So you have more evaporation there than anywhere else. The air heats up and rises. Now let's do it on the big picture. It heats up here, 10 degrees north, 10 degrees south, heats big time and moves up. When it moves up, it's got to go somewhere. Well, there's air all around it here, so it goes toward the poles. It rises and goes toward the poles. So what we typically have then is low pressure around the equator. And where that air comes back down, we usually have high pressure. Okay? And then you'll have variations in there. So the air heats up, rises, spread toward the pole, but doesn't make it all the way to the pole. The air cools, becomes more dense, and then it falls back. Sinking back to the surface at latitudes 30 north and 30 south. Right around here. Where do we live? 33 north. We're just above that. So that's what's been amazing to me in my physics classes. There's one of the classes that we do on thermometry, and you always have to adjust for pressure. So I always have the students, and most of them have phones, check and see what the barometric pressure is for Bessemer at that time. And I've just been amazed that almost always we're right at 1 atmosphere of pressure or a little above. And I would have sworn we should be a little less because we're at a certain elevation and the air should get less as we go up. I mean, the pressure should get less as you go up. But we're always right at and sometimes above normal atmospheric pressure. We're right at sea level pressure. Why? Because we're air at 30 degrees north. And the air is coming back down and we're in high pressure. Okay? So what's the end result? You have a band of low pressure near the equator and bands of higher pressure, 30 degrees north and 30 degrees south. That's where we live, just above that 30. We're 33 degrees, 23 minutes, 45 seconds north. Just right in that band. So these large convective cells form to equalize the pressures. You have low pressures here you have high pressures here, something's got to give. So you get these cells that try to equalize those pressures. If they're high pressure cells, they spin clockwise. Low pressure cells spin counterclockwise. Those are convective cells trying to equalize the pressure in between the two. And that's why you get all the storms. Most of your hurricanes in the summertime form over the coast of Africa in the low pressure area, but they form here, and then the easterly flow brings them across the Atlantic, and some of them make their way up the coast, some get into the Gulf of Mexico, some turn out to sea before they get to much land mass. These 4 islands down here just get hammered just about every one of them, okay? Cuba, Hispaniola, many of those get whammed just about all during. So the large convective cells. Okay. Kind of makes sense? Okay. So let's look at the concept of air masses. Okay. This is on page 572. What an air mass is a large, horizontally uniform bodies of air. So they're large layers of air, generally pretty uniform throughout the layer. Large, covering a lot of area. Okay? In them, the moisture and temperature conditions are almost equal. Okay? So you're not going to have any big changes within the large air mass. There are 4 main types. Now this is big types. There's smaller types, but these are the 4 big ones. You have continental polar. Okay? Where we live, we call them the Canadian air masses. Because they're continent, further north from us, they're generally cold, right? And generally drier. Okay? Continental polar. You also have maritime polar. Now, I don't know if you followed it, the big storm that went across the northern U.S., what was it, last week? Or earlier this week? And when it got out to sea here, boy, it picked up some moisture there and got some of the cold air coming down here. That's maritime polar. You get continental tropical. Now, we don't have any continental tropical real close to us, but Mexico sends that up to the U.S. Continental tropical. Then you have maritime tropical. Bingo! That's really us. We get Canadian continental polar coming down, and we have maritime tropical coming up from the Gulf of Mexico. Frankly, thank you, Gulf of Mexico. You keep us moist. You provide plenty of rain. You sort of moderate our temperatures. We get a little warmer in the winter than most areas should at our elevations and latitudes. And we don't get quite as cold in the winter because Gulf of Mexico is down there sort of keeping us. So for us, we get continental polar air masses coming in, maritime tropical. We're not close enough to get very much maritime polar, nor are we close enough to Mexico, though it can come up into Texas and then blow across us. I'm guessing that's what caused the drought last year. That continental tropical coming up, dry air, and then blowing over us and didn't allow the rain to get into us. Now, these dictate what they call the air mass weather. Big systems of weather. Weather conditions that remain the same over several days. And generally ours does. We don't have, the old saying is, if you don't like the weather, wait a day, it's going to change, Ours doesn't really change that rapidly, but when it changes, it changes pretty abruptly. But usually, like we've had, we're probably in the 60s outside now, is that right? I haven't been out since I got in this morning. I think tomorrow it's getting close to 70. So we're in a gradually changing, probably because our maritime tropical is winning, bringing in the warm, moist air. In a few days, then the continental polar is going to come down and probably drop it back again. So we're in the battle between these two and maybe a little bit of the others too. Okay, but usually the weather conditions remain the same over several days and then you have a change. The weather changes when a new air mass moves in or when the air mass acquires more local conditions. Like, when we get 70 degrees tomorrow, we should not be 70 degrees in February in Alabama. We shouldn't. That's maritime tropical sending us a lot of warm, moist air. When the amount of solar radiation we get and stuff is not enough to support that, it'll cool down gradually. Okay? So that's why it changes either when another mass comes in or when it re-equilibrates to local conditions. Now, the picture in the book is a much better picture than the one on this slide. It shows much bigger bubbles, okay? But here's your continental polar. These are your Canadian air masses. We call them anyway. Sometimes I actually call them polar air masses. If that comes sweeping through Canada, do you remember, was it a couple of winters ago, we had the Arctic vortexes? Okay. Boy, that was miserably cold weather then. Because that came flooding down from all the way from the Arctic Circle, and very little stopped it. And it had brutal temperatures down here. I really hate when that happens because I'm afraid the peaches are going to freeze and Florida is going to freeze and there goes the strawberries. I love my fruits, and nuts, okay? But anyway. Over here in the upper here, this is what I was talking about this, earlier this week when the maritime polar, those cold, wet temperatures come in here. Maritime polar here. Now, this isn't quite so polar, but it's a little bit. But this is where Washington State and Seattle gets so much moisture here. I'm not doing that, okay? It's just shaking on its own. Maritime tropical here. This is what surprises me. Quit doing that. In Mexico here, right below California, is the Baja Peninsula, okay? And it's surrounded on three sides by water, and it's almost a desert. How can that be so dry? Because that maritime tropical just doesn't bring in a lot of moisture water. It's mostly continental tropical pushes that out. And that's called the Gulf of California here, though it's not in California. And to me, that looks like that's the end of the San Andreas Fault, but it may not be, but it looks like it would be. But here's Mexico underneath the southwestern U.S., and that's what keeps this area very dry here. But thank you, Gulf of Mexico. We have the maritime tropical, and we just keep the moisture pumped up here, especially at this time of year. In the summertime, sometimes the continental tropical keeps us too dry. Most of the other goes up here, but that's what keeps us from being a desert. And then over here, maritime tropical here too. The bigger air masses. And it's when they collide is usually when we have problems, like big storms. And these will cause our weather fronts. The front is a boundary. How are we doing on time? The front is the boundary between these air masses at different temperatures. Let's get a picture here to help. If my memory's right, this is not a particularly pretty picture. Sort of hard to see here. And you can't really interpret this without a little bit more thing. The last lab we did, remember we were doing topographic maps, right? And those little gray lines y'all were looking for with such vigor, those were called, I don't know if you actually gave the names, they're called contour lines. But what the contour lines were lines of the same elevation. Same means, there's a prefix that means same, and that's iso. So what you're looking at there were isoclines. Cline meaning inclination. In other words, they're all at the same inclination, isoclines. Those are your contour lines. And some of you noted on the Devil's Tower, you know, what the gradations were. And some of you had 50 feet per circle, and some may have had 20. I don't remember for sure. I read the layout, so I've forgotten that. Well, on this map, those lines that look like they could be contour lines, they really are contour lines, but they're not measuring elevation. These are measuring same iso bars, barometric pressure. So this line right here, all along here, I can't read the numbers, they have the same atmospheric pressure. Here it has the same atmospheric pressure. Here it has, I wish I could read that. And I think this is a figure from the previous edition, so I don't have it in my book, so I can't read those numbers to you. But these are the same, okay? And all around here, the numbers are getting higher and higher and higher. This is sort of like a mountain on your contour maps, but this is high pressure. Up here, you see, though, these are low. These are decreasing as you're moving in. That means this is a low pressure system, okay? And that's a pretty significant low pressure system. I have a feeling that's one of what they call the nor'easters. Pretty big storm that's coming down there and bringing, depending on what time of year this is, it could bring in snow or it could be bringing a lot of rainfall to the Nova Scotia and New England and maybe points beyond. Okay, so what are your fronts? That's when these things have collided. Here we have maritime tropical off here and continental, probably polar, coming in here. The boundary line, these are the fronts. And it looks like this is a cold front pushing through this way, pushing out the warm, moist air, and because this is colder, denser air, it's undercutting that. Well, when it's undercutting it, guess what, folks? You have a weather situation. You're probably going to get a fair amount of rainfall along that front because the warm, moist air is down here. The cold, dry air is here, pushing this up. This warm air is going to condense, and then you could probably have some rain or storms there. The trouble is, this is a pretty weak-looking low here. Where they meet, that's a pretty weak-looking low pressure area. And by the way, low pressure, the winds go counterclockwise in the northern hemisphere, and around high pressure, they go clockwise. You go to the southern hemisphere, they reverse. Okay? So, up here, going counterclockwise here, clockwise here, you're going to have a lot of wind in between. And the other thing where the lines are close together, your pressure changes are happening very rapidly. That's like a steep slope on the contour maps. That's going to be a very windy area on your barometric maps. Okay? But this, by and large, except for that one low up there, it's a pretty calm day. Okay? Not much happening. Because one thing, you see a lot more high pressure areas here, and only one significant low, well, a little low right here. And there's one here, but it's not, they're just not very strong. There's not many lines around them, okay? But you do have a few. But these are the fronts, which are where the air masses collide. So the cold front is where the cold air is moving in, displacing the warmer air upward. The moisturizing air cools, leading to large cumulus and thunderclouds. You're going to have rain most of the time. The warm front is when that would be the reverse of this. It may be this one. Your warm air is pushing the colder air back up, okay? So that's a warm front. The warm air advances over the colder air mass. Now in these, here's a key difference here. When you have a cold front moving in, this cold air mass undercuts the warm, moist air, and that rises pretty quickly. And that rapid rise, that can create your thermals, and you can get some spin, you can get some pretty nasty weather, thunderstorms, tornadic activity, or something like that, okay? And that's pretty dangerous. Those are your unstable air masses, okay? Whereas the warm front, that's the cold front because cold air mass is pushing the warm. On the other hand, when you have the warm air, it's not picking up the warm one. You're going to have to look in your book for this one. Okay. The order is not quite the same. In fact, let's deal with the cold for a while. Don't go to warm yet. Okay. Here's that cold again. Okay? Still here. The cold air mass, notice it's a real rapid increase here that forces the thermals up here. That forms these big cumulus clouds. Now this is where I regret that we had to skip the last chapter. But the last chapter was so long. That talks about the atmosphere, and you would learn about these clouds. That's a cumulus cloud. That's your big rain producer. If it's big enough, it could be a big hail producer. If it's strong enough, it could be a big tornado producer. I mean, those are the, I like to see them because they bring rain, but they can also bring some pretty rough weather. But the cold air is forcing this up, and the steeper that front is there, the more the thermals are created, and you get the spin coming out of this, and your ice crystals way up high here, they're falling, and if that thermal convection is pushing them back up, those could be big hailstorms, and they finally fall and could do a lot of damage. But most of the time, the ice crystals form, and they fall. If it's wintertime, that would be snow, but most of the time here in the southeast, winter or summer, it's going to melt on the way down, and you're going to have rain. And that is a major rain producer. And the key here is the cold air mass. That's a very steep front. Okay? Now, here it is. I just didn't go far enough. Here's the warm front. The warm air mass is now moving in. Cold air was in place. The warm air doesn't bulldoze its way in like the cold does. It just sort of pushes its way in, and it makes a much more gentle gradient here. And that gentle gradient is going to move some warm air above the cold air, and you will get some rain. A lot of times the rain will be in the colder region first, and the warm comes later. I'm trying to think. I think the last rain we had was that way. It started raining when it was rather chilly, and then by the time it quit raining, the temperature was warmer, because that was a situation like this. The warm air mass won over, and you create this. Again, you have cumulus clouds, but look here. Those were 5 kilometers high. The ones in this one were 15 kilometers high, okay? Much bigger, stronger, more forceful, a lot of convection in those, okay? Here, not nearly as tall, so that's mostly probably going to be coalescence of crystals. I don't think they even get cold enough. Some of them could have been ice crystals, but that's just coalescence there. Does that make sense? Now, there is another type of front shown here, but they don't have, shown on this slide, but they don't have a picture of it. This is called a stationary front. And this is when the forces influencing the warm and the cold air masses become balanced, and nothing happens, okay? They just sit there. And occasionally, that will happen, and you'll get day after day after day after day of rain. You're in a stationary front, the warm air bringing up, pumping up the warm, moist air, hitting the cold air and it's raining, but it's not pushing it out of the way. The forces are kind of balanced, so it just sits there and rains. Now, that sounds pretty good unless it happens frequently enough, you start getting flooding. And that has happened, maybe not around here recently, but it has happened. Just one of the last storms that went across, it just dumped an awful lot of water. In California, in the West, where they had been so dry for so long, it just sat there on top of them and rained and rained and rained, which was good. In some places it was snow, snow, snow. And those who went skiing, a guy from our Sunday school class went to Salt Lake City and did some skiing last week. So he took advantage of that fresh snowfall. He was a retired surgeon, so he had plenty of money and time. So he went up and went skiing. But it created some problems because they had some pretty major flooding in some areas. So the stationary fronts, if you're in a drought and one of those comes by, you say, thank you very much. If it lasts too long, you say, get on out of here, okay. Now, sometimes those stationary fronts could be dry fronts, though, and those you really don't like to have when you're in growing season because you don't get any rain out of them. So, all right. They didn't show a picture of that one, though. Now, while I'm here, and by the way, your book, if you have the newer edition, rather than the slide we had back here, that slide, you have more of a invented slide, a drawn slide, not an actual one, and it shows the various fronts, and it also gives the barometric pressure. Now this is, I think these are in millibars. I believe what these are measured in is millibars. And that's sort of an idealized situation, but it could have happened, okay? Then, now this is an interesting one. On the top of my page 575, it should be there, about science and society. Have you heard anyone talk about heat islands? Ever heard that phrase? Okay. And in the book, it has urban heat islands, and those are usually urban areas. Now, we're not in any major urban area here, but we do have, Birmingham's a reasonably sized city, okay? And I have had some nights, especially fall term, toward the end of the term, second mini term, November, December, it can be getting sort of chilly on those nights. And I have left here, and usually then my class goes, seems like I get through it, 7:45 or 8 or something like that, 8:15, somewhere in there. Go out, and it's been pretty chilly out. Okay, I get in my vehicle, and it has a thermometer in there, and it indicates I'm going to pick a temperature. Let's say 40. It'll be 40 when I get in the vehicle. Now, I get on the road, and I'm traveling north and east, going toward Birmingham. North, you would think, if anything, I'd be getting a little cooler. East, if anything, you would think I'd be getting cooler because the sun went down there a little bit earlier than it went down here. So you would think both of those would contribute to cooler temperatures. And it's getting later at night, longer since the sun went down. So you would think the temperature would be falling. And sure enough, I'll read my temperature as I go along, especially if there's not much traffic. It'll be 40, and then it'll drop to 39, and then 38, maybe even to 37, okay? Maybe not too many more than that, until I get on the outskirts of Birmingham. I start getting into Inslee area or Fairfield, some of those, Fairfield first, then Inslee. But then, and suddenly the temperature starts going up. I'm still going north, I'm still going east, it's still getting later at night, but the temperature is rising. Why is that? Because Birmingham is a larger urban heat island. Okay? Why would that be?
Got a lot of buildings and machinery.
What's that again?
Got a lot of buildings and machinery.
Okay, more buildings, absolutely. Okay? More buildings, which means fewer trees. Trees moderate temperature. Less grass. Grass moderates temperature. Asphalt, cement, buildings, and guess what? Those buildings, if they're producing heat, like they're heating themselves, they're exhausting heat, heat's coming out of them. Or in the summertime, they're air conditioning, but guess what's happening with air conditioning? You ever go out and feel the unit outside when the air conditioning is on inside? Really hot coming out of there, okay? Because you're compressing a gas, making it hotter, blowing the heat off the gas, and then letting it expand, that cools it off inside. So you're exhausting heat. So every system going is making it hotter. You have more cars, you have more everything to produce more heat in the heat islands. And sure enough, that's true. I would see it driving, and Birmingham's not a huge city. Atlanta would be even more than Birmingham. New York, Los Angeles, I can't even imagine, okay? Houston, huge heat islands. So there's a nice little blurb there. It's pretty short, but it does have some questions for you to take a look at. Okay. All right. Now, there is another set of figures in your text that I think show up a little out of place on the slide set. Yeah, here they are. And it's okay because they really go together all right. But this is talking about waves and cyclones. Now, the text begins on page 576 in my book, but the figure that you see that's going to be on the next slide is on the previous page, 575. So it looks like it's out of order, but it's okay. It's talking about the same thing. Okay? Waves and cyclones. Now let me give you a little story on this one too. Before I started teaching in the two-year college system, I had worked for 8 years, I think it was, at Southern Research Institute in Birmingham. And I was in a group that we did mostly radon research, so I did some other air quality stuff too. And we had set up actually another group of scientists had set up a building and had it built down in Florida that they were trying everything to control as many of the factories as possible. It's hard to do a lot of good quality research in someone's home because people are coming and going, leaving windows open or doors open or airing things out and stuff. It's hard to measure and know what's going on. But here we had this building that no one was going or coming except maybe once or twice a day when the technician would go in and check on all the equipment, which she was very careful about. She was actually an engineer, careful about closing doors, keeping everything steady. And we were getting the data. We had a data logger in there, and she would send the data back to us, and I was analyzing it, and looking at it, what's going on. And one day, our radon level, we were studying radon, the radon just shot up in that building. And didn't seem to be any reason for it. So I started looking at other data, and sure enough, I looked at the pressure, barometric pressure outside. We had a little weather station there. It had taken a dive. And so I tried to check other things, and I mean, it was major, it was huge. I thought, all this equipment couldn't have gone wrong at the same time, because they are separate from each other. What is going on here? So I called Jerry Tracy, because I knew him. He said, the odds are you had a tropical wave come through. That was the first time that I could remember hearing the term wave, and it wasn't talking about a water wave, okay? This was in Lakeland, Florida, or actually Bartow, Florida, down in the middle of Florida, so it wasn't talking about that. So what we're talking about now are going to be waves and then cyclones. So what's the mechanism here? Okay? The bulges or the waves are often formed between oppositely moving air masses. Now what had happened here was, I guess there had been probably a continental, I wouldn't call it polar, because this was down in Florida, but a continental air mass sitting over Florida. Pretty strong sitting there. And then here came this low pressure, but maritime tropical system that came pulling its way in there. And the bulges or the waves often form between those oppositely moving air masses. The overriding uplifted cold air, now this is a bizarre statement here. The overriding uplifted cold air, that shouldn't happen. That the cold air shouldn't be lifted. The warm air should go up and the cold air go below. But the overriding uplifted cold air produces a low pressure area, and the further cold front motion leads to an occluded front and a cyclonic storm. Now, those are a lot of blah, blah, blah words. And if you think they are bad, wait till you see the slides. But we are at 3 o'clock, so why don't we pause right here? I should have done it before I started this slide. And let's take a maybe no more than 5-minute break, get up, move around some, use the restroom, whatever, and then we'll come back and I'll call roll again and we'll go from there. Okay? So let me put this on pause. All right. We led off about waves, talked a little bit about it. As we said, it's bulges or waves often form between the oppositely moving air masses. The overriding, and this is the weird part, uplifted cold air produces a low pressure system. Now, why would that be true? Well, cold air sinks, so the pressure decreases. Further cold front motion leads to an occluded front and then to a cyclonic storm. So here, like I was saying before, while these words are sort of blah, 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 the pictures aren't much better. Okay, they say pictures worth thousands of words. There's just more of this. So here's what we have, and it's a weird situation. It's not what you would expect it to be. You have the warm air down here and the cold air up there. Not a good situation, okay? Because the cold air wants to be down, the warm air wants to be up. So as it's moving like this, the cold front moving in like this, the warm front's moving this way, so the cold front is on this side, the warm front on this side because they're moving like this. The warm air tries to push its way up, and the cold air pushes down, so you get, this is the bulge they're talking about. The bulge or the wave often forms between the oppositely moving air masses, okay? Now, the overriding uplifted cold air produces low pressure. And this is what we see is happening here. Now here's the other thing. I don't know, you may not have seen this illustration before. Are y'all hot in here? Okay. Is it warmer or colder outside? If it's warmer outside, keep them closed. But if it's cooler outside, let's get them up. Okay. Now, I want to ask you a question. If I were to hold this piece of paper here and blow underneath it, what's the paper going to do? It's going to go up?
It's going to kind of go
Yeah,
up.
it is, right? Pretty obvious. What if I blow over the top of the paper?
It's going to go down.
Oh, okay. What in the world is happening there? Okay? All right, here's Terry. I thought he would be back. Okay. Terry's back. But we still lost Josh, huh? And Emmanuel. Still lost. Well, hopefully he'll be back. All right, so what in the world is happening here? Well, we know what's happening here. I'm blowing, and the greater pressure down here and more velocity pushes the paper up. That makes sense. But what in the world is happening here? Why is that lifting? Okay, there's a feature, and this is all fluids, and you probably all experienced this in one way or another. The more rapid the velocity of a fluid, that drops the pressure. Okay? Have you ever been on the interstate, maybe stuck over in the right lane, and a big old semi goes roaring past you and felt the car pull toward that? Increased velocity of the air decreases the pressure, you're actually sucked toward it. Okay? Have you ever used any of those devices, either for washing windows or washing cars or just about anything, where you run water, you have the soap down here, you hook the hose up, you pull the trigger, and the water goes going by, and it sucks up the soap and blows the soap out, too. Same thing. The increased velocity of the fluid decreases the pressure, and it creates a vacuum, sort of. Okay? Y'all know anything about carburation of cars? That's the sort of the same thing there. You call it a vortex thing. The air moving past sucks the gasoline into the carburetor. They don't use these much more anymore. Most cars have fuel pumps on them now, so you don't count on that vacuum anymore. But they used to do it that way. That's how it was done. It's all over the place, whether you realize it or not. Did you have a question, or you just moved around?
When you asked if we had used the pump thing.
If what?
When you asked about the pump thing.
Oh yeah, right. I'm sorry. Okay. Yeah. Yeah. Okay. Okay. Yeah. So that's what's going on. So you have this cold air. Now you have this bulge here, and the cold air is moving more. It has to increase speed to move up here, and when it increases speed, it reduces the pressure. So that's why you have the low pressure. And it's happening more so over here, and you see the warm air here is trying to force its way up. The cold air is going up above, but by going the extra distance, it creates a low pressure. And when that happens, ultimately, in this picture, I guess it makes sense. It sort of seems like these two things coalesce into this, and that's called an occluded front. This is where this illustration really leaves a lot to be desired. They don't give you a real good definition of what an occluded front is. We haven't mentioned that before, and this picture sure doesn't say much to me. Now, maybe y'all see it, and it makes sense to you, but I can't do much there. But anyway, this creates a low pressure area, okay? And the low pressure area then is the thing that sucks up the air from beneath. The warm air goes flowing up, and that's your unstable situation. So the air starts moving like that, low pressure area, in the northern hemisphere counterclockwise, and the southern hemisphere clockwise. Now, I told you the story of the physics professor going to Buenos Aires, didn't I? I told you that one? Okay. First thing he did, the party city of the southern hemisphere, got there for meetings, and what did he do? He went running into his hotel room so he could flush his toilet and watch the water flow in the opposite direction, because he's in the southern hemisphere. That's how weird physicists are. Okay. So what you form then, after you form the occluded front that turns into a cyclonic storm, doesn't have to be a cyclone yet. What a cyclone is a low pressure area with inflowing upwardly forced winds because of the low pressure, and those are warm, moist area underneath. The circulation patterns caused by the Coriolis effect. Now, didn't we mention that before, Coriolis? Okay? And Coriolis of force is when you have any kind of motion in two dimensions, you create a torque in a third dimension, and that's what creates the movement there. So, trying to think of a practical example of this. I can think of some, I don't know if they're very practical. The bombardiers in planes dropping bombs from way, way high. If they drop them, they think straight down, not going to hit the target, okay? Because lots of reason, but you also have the twisting force, so they have to put that into the equation too. So they have computers, gunfire control directors, that figure all that stuff out for them. Boy, there's so many variables. So it's not at all surprising that you have, what do they call it, collateral damage, unintended target hit. They've done all the calculations, something changes, and a little bit of change can make a really big mistake. Or human error too can make a really big mistake. So that's what the cyclone is, a low pressure area inflowing upper force wind, circulation pattern caused by Coriolis effect because of basically by the spinning of the earth. Now the anticyclone is a high pressure area, okay? Here the air turns clockwise direction when seen from above. The air sinks, is warm, relative humidity is lowered, and you tend not to have any rainfall in a high. Now, I don't know if you remember ever hearing them say this, but I lived on a farm growing up, and there was a couple of summers that just were miserable because we just could not get any rain, and they blamed it on a Bermuda high, okay? Almost sounds like some sort of drug experience, but that's not what they were talking about. And evidently some high pressure area over the coast of Bermuda, the way high pressure goes in a clockwise direction, I still don't see why that wasn't bringing us some moisture. But they said that Bermuda high was keeping, well, I guess what it was, the high pressure over Bermuda, all the weather systems then had to go above it. So all that rain would always head up the Appalachians and miss us. I got to hate Bermuda highs, okay, because we had just a miserable, miserable year that year. Is this in any way I can set it there? No. Okay, so that's what an anticyclone is. In the northern hemisphere, clockwise flow, the air is pushed down. That's what makes it high pressure, and relative humidity then is lowered. You're not going to have any dew points reached. You're going to be dry, fair weather for that. Okay. The book does a pretty good job of talking about it. It probably does a little bit better on the occluded front than this does, obviously. An occluded front is one that has been lifted completely off the ground into the atmosphere. The disturbance is now cyclonic, and that's what they're trying to show there, and it's just not really clear. I guess they're saying this is, whereas before that was your dividing line between warm air and cold air, now they're, well, I guess it still is. And the low pressure is lifted up, and the warm air is still going under, and now that allows the warm air to suck the warm air up. Not a great definition, I don't think. Okay. Now, this is an interesting picture, and it's very relevant, okay? But it's not really all that clear what they're talking about here. This is a map of the U.S., obviously, okay? These are the most common patterns for cyclonic activity, okay? Now, all the eras are about the same size. They shouldn't be. Historically, this has been the worst path. This one through Oklahoma, or this one up here through Kansas and Missouri and stuff. These have been traditionally terrible, terrible pathways where the tornadic activity follows. Okay? Basically a path similar to that. However, what was the year? What was it? May 11th? 2000, what would that have been? 14, 13, 14? April, okay, when we had this big Tuscaloosa, just all up and down the state. More tornadic activity than the whole country usually sees in a decade. You know, we had in the state of Alabama in one day. It was just incredible. It followed this pattern kind of right here, only it was much wider, okay? It almost went between all of these. They had tornadoes all up and down the state of Alabama. Up here, what were some of those towns up here? Phil something. There was a town somewhere here that just, the whole town got blown away. Goodness, I can't think of, how does it go?
Hattiesburg.
Not Hattiesburg, that's in Mississippi, but it was a name similar to that. I can't think what it was. That town almost got blown away. Tuscaloosa, huge damage, all down there.
Pleasant Grove.
Pleasant Grove got hit, whammed really badly.
Yeah.
And we went the following weekend. We have lake property up in Winston County, and so we were going up to check on things, and it was just unbelievable. As we were going up, you see swath after swath of where these tornadoes had gone through, just knocking down everything. Big, long, wide swaths, just total devastation. We went past a place that was trucking, and there were the trailers from the tractor trailers, just like dominoes, like someone had just toyed around with it. It was incredible. But we can't toy around anymore because Emmanuel's back. Okay. Everybody's back except Josh, and I guess he's not coming back. Sounds like it. Seems like it anyway. So these are just, and this isn't hard and fast. Nothing's fixed. But you would think, wow, what patterns we have here. And this one, though, that one, and by the way, we went that spring, it was the next fall, the class went to the Weather Center at NBC 13, and Jerry Tracy told us about this sort of an index the weathermen use. They look at several different factors. And quite often, sometimes in the upper atmosphere, it looks like you're bound to have tornadoes, but on the surface, conditions aren't right, so they cancel out. Or on the surface, things are right for a tornado, but something about the airflow up top wipes it out. He said this day, every measure that they took was favorable. And the index just, he said they had never seen a number that high before. He didn't even think they could have a number that high before. It was in like the 400s or something like that, whereas normal would be 50 or 60. I mean, it was just, I don't remember exactly, but it was, he said we just didn't know what to say. We didn't know what was going to happen. We just knew it was going to be bad, you know, and it was really, really bad. Okay. Did I turn the wrong way? I think I did, yeah. Well, no, I was going the right way. It just went back to nothing there on the slide. Now, here's what I think should be there. I think they're missing a slide here. I think this figure 2314 perhaps should be there. It shows the air sinking over high pressure and being uplifted in the... So if you got your books, in my book it's 2314. It's just really close to major storms. Okay? If you've got that in your book, that's, I think, the figure that should be there. What's that? Oh, did I do that? Okay. Now we're moving into major storms. Hopefully not today, though. Okay. Major storms are rapid, violent weather changes, okay? Often associated with those frontal passages. Remember what the fronts were? Where two air masses have collided, okay? And the front, one or the other, is doing. So these are the major storms. We're going to look at three major types, from powerful to more powerful to most powerful, okay? The smallest of these that we're going to talk about today, though you can have smaller ones, are thunderstorms. Okay? Pretty common, and I just couldn't believe it. What was it? A week and a half ago, we had a really major thunderstorm in early February. This isn't the time of year when you're supposed to have thunderstorms, okay? And yet we had one, okay? Later we'll talk about tornadoes and hurricanes. Let's start with the thunderstorms. Did I go 2 slides? Okay, I did. Okay. Thunderstorms usually develop in warm, very moist, and there's that unstable air. Okay? 3 stages. They love 3 stages, don't they? Okay? The first is a cumulus, and this is associated with that convection that you have going on. Low pressure, convection, the warm air rising, warm, moist air rising. Now, this could be associated with convection, mountain barriers, cold front, whatever is creating the change. Remember, violent because of a change of conditions. It could be because of convection, a mountain barrier, or a cold front. Now, I don't know if you've followed much reading of explorers who try to climb, say, the Himalayas or Mount Everest or some of those mountains. If you read any of those stories, you see conditions are so iffy because you can have these violent storms just come up in no time because of those mountain barriers, okay? And it's hard to predict. And you sure want to know in plenty of time because it takes days to get up there. And in addition to that, you have to stop along the way. You have pressure changes. It's just like when you're doing deep sea diving, you can't come up too fast because you'll go through what they call the second? Yeah, it's a pressure sickness. Yeah, it's exactly that. They have another name for it, and I just can't think of it now. The bends, that's what they call it.
Yeah.
And basically what causes that, you have air dissolved in your blood, obviously, because you're pumping oxygen to all parts of your body. So air is dissolved in your blood, and when you're under large pressure, the air is smaller size. Those little pockets of air are very small. If you come up too fast, see, going down doesn't bother, okay? You just adjust for it as you go down. But if you come up too fast, that air in your bloodstream suddenly expands in volume, and you can burst capillaries. The capillaries is where the action is. That's where you exchange your gases and fluids and stuff like that. That's all at the capillary level. You start bursting capillaries, you bleed to death internally. And that's what the bends is, pressure sickness. And if that happens too big, you're out, you're gone, So that's why deep sea divers have to stop at levels and hang around for a while, let the blood equilibrate again, the blood gases come up, and depending on how deep they went, they have to take more and more time coming up. Well, the same thing in mountain climbing. Now you're going from high pressure, lower, lower, lower. You have to stop sometimes for as long as a week, 3 to 5 days or a week, to let your body adjust to it. And then you move on. Well, guess what? Climbing Mount Everest, I think there's at least 2 stops. So how can you predict the weather 3 weeks down the road? You can't. Here in Alabama, 3 days is about the best we can do. We'll get to that later. A week, those 7-day forecasts, they're dreams. Okay, it's almost science fiction. Hopefully you've forgotten what they predicted it would be a week ago, because they've updated it since then. Yeah.
I heard the weatherman can be wrong every day and it's still on fire.
Well, I hope teachers can too. Yeah, well, actually,
I thought
those.
you could fire them.
What?
Like after they get so many wrong, I thought that's when they get fired. After they get so many predictions wrong. No, that's not the weatherman. That's the, you know what I'm talking about? Yeah, never mind.
All right. No, the weathermen, they use the National Weather System, and then if they want to make any adjustments, they can, because they're all meteorologists, or most of them are, and they know what they're doing. but the weather changes so rapidly it's hard to do. So anyway, that's the first. The cumulus phase associated either with convection, mountain barriers, or a cold front. Then we have the mature stage. They like that as a middle stage, don't they? The updraft can no longer support, okay, let's get some visuals in here. Here's the cumulative stage. You're updrafting either by convection, the mountain barriers are cold front, you're sucking air up, and it's just heading upward. You're forming taller and taller cumulus clouds here. That's why they call it cumulus. The mature stage, the updraft can no longer support, because as you go in, you're bringing warm, moist air up, it's cooling off as it goes. Those ice crystals start forming, but they're tiny, they're ridiculously small to begin with, but they keep growing, and the further you take them, the colder and the more they grow, and after a while, the updraft can no longer support the growing ice crystals and snowflakes, and they start falling. Okay? That's when the rain begins. Or if you're in the wintertime, snow begins, if you're further north than us. Okay? And that's when it happens. Now, the falling frozen water melts and becomes rain. That's what happens down here. Further north, it never gets warm enough to melt, so it falls as snow. Hail formed throughout the ice accumulation process. If these are really big, really tall, and you start getting the repeated updrafts, then that hailstone gets bigger and bigger and bigger, and finally when it releases and falls, it doesn't have time to melt before it falls, and you get hail while it's raining. I really don't like hail. There goes the peach crop. There goes other crops, you know. I hate it when my peaches get damaged, okay? I love peaches. Okay, and then your final stage, all the updrafts are exhausted, and you just continue rain, and it plays itself out. So that's the final stage. Kind of makes sense? Okay, that's your thunderstorm. Now, what happens? Why do they call them thunderstorms? Easy question. Why do they call them thunderstorms? It thunders. Now, if it thunders, why does it thunder? What has created the thunder? The lightning. If you hear thunder, it's lightning somewhere. You don't have thunder without lightning, and you don't have lightning without thunder. Okay?
What's the science behind it?
What's that?
The science behind
What's the science behind it?
lightning.
Yeah.
With
Oh,
lightning
lightning.
strikes.
Okay, let's start with lightning. Okay? All right. In a thunderstorm, you have lots of movement. We saw that in the last slide, right? Air's going up, grass coming down, lots of movement. Whenever you have movement, electrons tend to be knocked off or gathered, okay? From air molecules or ions or whatever, okay, becoming ions. Well, usually the positives, for some reason, accumulate in one place, negatives in another place. And the potential difference grows between those two. And when finally there's enough potential difference, the air can't support that potential difference anymore, because air is really a pretty lousy conductor, right? So it's a lousy conductor, so it supports a pretty big potential difference. At some point, it can't. And you have sudden, abrupt electrical discharge. Just all of a sudden, that's lightning. And when you have sudden, abrupt electrical discharge, you have a mass of very high energy ions flooding, electrons basically, but it's, conductor, moving through the air. As it does, then that's hot. I mean, there's heat, there's expansion, there's a lot of energy given off, and air suddenly expands. And then when the lightning goes, it contracts again just about as quickly. That's what causes the thunder. Okay? That pressure wave of an expansion and a cooling. Whoa! You've just made a big pressure and what they call rarefaction right behind the pressure. That's what makes thunder. Okay? Won't sound quite gross mine is, but yeah. So is that what you meant? The science behind it? Okay. So the updraft, downdraft, circulating precipitation separate the electrical charges. I didn't know it was on the slide here. It separates electrical charges. The charges accumulate in different parts of the thunderhead. Okay? And then what happens if you have a big enough potential difference build up, suddenly the air can't support it anymore, and you have a discharge of lightning between the charge centers. Positives going to negatives, or negatives going to positives, or something. The discharge, okay, now get this. I don't know if you've seen it before. I'm sure you have. But it happens so quickly you may not have realized it. You've certainly seen what they call cloud to ground lightning. You have a a charge center up here, build up either positive or negative. No, negative. Build up negative here. And the Earth is pretty much neutral, but there's still a big potential difference between big negative and neutral. So all of a sudden those electrons make their way to the ground. That's called cloud to ground discharge. Believe it or not, though, you can have a very big positive center up here getting closer to the ground, and the ground's neutral, but it's still a big potential difference, and you can actually have discharge going from ground to cloud. Now, unless you have a slow speed film, I think is the right way to say this, that you can capture something and spread it out over time. And I've actually seen things when they have done this, and you can see that lightning starts at the ground and goes to the cloud. Usually it happens so fast you don't see where it starts and ends. You don't even know where to look. It just happens. But if you happen to have your camera there and activate it right when it happens, you can see that go up. Okay? Or you can have cloud to cloud. Now, I remember one night when I was in the Navy, it was what they called the dog watch. Usually you had 4-hour watches, midnight to 4 in the morning, 4 to 8 in the morning, 8 to 12 in the morning, then 12 to 4 in the afternoon. But then you had a dog watch. And what that was, one, you had just a 4 to 6 and then a 6 to 8. That allowed the people who had the 6 to 8 to eat early before they went on watch. Well, allowed the people who had the 4 to 8 watch, they could still eat when they got off watch. So they split that up so everybody could eat. But the others, 4 to 8 in the morning, you ate when you got off, you ate before you went on, But the evening meal was right in the middle of the 4 to 8. So they split it up that way. And I think it was a dog watch. It was early evening. I think it was the second one. I went up to stand duty on. We were out in the middle of the ocean, no other ship around. And it was a cloudy day, and there was wind and stuff. And literally the whole 2 hours, it was a spectacular spider's web of cloud-to-cloud lightning just going on continuously for almost the full 2 hours. It did let up toward the end. I've never seen anything like it in my life, and I can't begin to explain what could have caused it. But I mean, it was just like a network of lightning. It would ease up a little and then come back, and then it was the prettiest, one of the prettiest things I've ever seen. Cloud-to-cloud lightning. Okay. Then you have and here's what I was explaining before. The expanding pressure wave from the heated air produces the crack of thunder. You have first an expansion when the lightning goes through the air. It heats it, it ionizes it, everything's happening as it goes through, and then it collapses, and that's the pressure wave. Big pressure, and then it collapses. Pressure, rarefaction, that's your sound wave that is the thunder. Okay? Here is sort of the picture of that. Here you have this is so hard to teach from here. Here you have, remember in the cumulus clouds you have just motion going all over there. Updrafts and downdrafts and all, you got motion everywhere. And for some reason you get negative charges on some parts, positive charges at other parts, and then you have other clouds nearby. And now there's two things that's going on here. Okay, first, the charge accumulation, and the other thing is the distance. Both of those come in. The larger the potential difference, the more likely you have a discharge. But also, even with a smaller potential difference, if they get close enough, you'll have the discharge. Okay? So both the charge differential, and the distance, they come to play. So when this negative gets too close to the Earth, now the Earth is basically neutral, but you see a negative charge is going to attract positives, and when that potential difference gets close enough, this is cloud to ground. It charges the electrons go to ground. Okay? But over here, where you have positive charges accumulated, if that gets too close to ground, the positives have been attracted here, the negatives are attracted over here, and now you have ground to cloud. And you're not going to be able to tell it with your eyes which one of these it is, unless it's a really long street, which that would be a lot of potential difference. And then you have cloud to cloud within one cumulus, or cloud to cloud across two clouds, okay? And it always goes negative to positive, negative to positive. Everything else in nature goes positive and negative, except the electrical charges, they go negative, because the electrons are negative. They're the mobile charges. Positive charges tend to be not as mobile. And it's probably Benjamin Franklin's fault. Someone said he's the one that said, well, let's just call electron negative, because everything's backwards, okay? But I don't know. It may not have been. All right, so that was the strong storms, thunderstorms. Then, if you have a tornadic storm, you're in pretty serious problems. It's the smallest, usually smaller than a thunderstorm, but most violent weather disturbance happening. Much smaller than a hurricane, much less energy, but because it's so small, the violence is just many times more violent than a hurricane. Hurricane will cover a much bigger area, of course, and actually spawn small tornadoes, but the tornado, where it is the most violent of all the storms. Rapidly whirling column of air, okay? If you saw the videos and the news coverage of those tornadoes, you saw huge chunks of debris just being thrown around, trees being sucked up and thrown around like they were toys. It's just incredible. So rapidly whirling column of air, usually of diameter 100 to 400 meters. Now what's 100 meters approximately? Something you're familiar with.
A lot of football.
A football field length is a little over, like from the goal line of one to the back of the end zone of the other is about 100 meters. Okay, so that's a pretty wide, that's the length of the football field. 4 of those together, guess what? You're pretty close to a quarter of a mile there. Okay? 400 meters is awfully close to a quarter of a mile wide. Guess what? There have been tornadoes as much as a mile wide. Oklahoma has had some of the, I know, it's hard to believe. Some of those in Tuscaloosa were close to that too. Because we were, that next summer after the storm, see, what was it? We were on our way to see Karen's brother in Louisiana, and we were taking her sister. Her daughter was in a cheerleading camp in Tuscaloosa, and we were taking somebody, maybe the father or mom or somebody, to go to it, because they already were over there, the others were over there, and we had to drive through Tuscaloosa to meet them. And literally there were areas, and Karen said, I can't believe this. I've never seen, I think it was Druid Hills Hospital. She said, on this road we're on now, you couldn't see Druid Hills. There was just too much in between. And there was nothing but level lot. That was all in between. Everything had been torn up for block after block after block. Wherever we were, I don't remember what the name of the street was, you could see the hospital, because everything else had been wiped slick. unbelievable. I don't think it was quite a mile, but it was more than 400 meters, I'll put it that way. Wind speeds up to 480 kilometers per hour. Multiply that by 0.6, you got about 250, 275 miles per hour. Wind. Unbelievable. The damage produced by several things. Number one, of course, the high winds. Okay? That wind, a wind of that speed, can pick up a tree or a car or something else and throw it through a window. I mean, so the wind is going to produce a lot of damage. But even worse than that, unless something comes flying through a window, where does the glass go in a tornado? Outside. Because the pressure drop on the outside is so much more than the inside, you blow up. They blow out. And literally, things are thrown out. Not just glass. Roofs are lifted off the houses. It's not that they're blown away. They're lifted off the houses. And sometimes, and this really happened too in those tornadoes, the houses are lifted off the foundation. And some, I've seen pictures, the house has been lifted up and twisted a little bit and sat down. It's not where it was before. The whole house was lifted, except the foundation stayed in place. Unbelievable. So drop in pressure at the center, and of course the flying debris, which also, that's from the high winds as well. And the high winds are from the huge, huge pressure difference. They're associated with the very most intense thunderstorms, and it seems like most of the time they precede the storm. Sometimes it may be after, but see, if a thunderstorm hits, a lot of the energy is lost there. Remember back several years before that line of storms, there was a tornado went through Oak Grove, wasn't it? Wiped out Oak Grove High School?
Oh, yeah.
Remember that one? Okay. I was here teaching. Okay. Oak Grove is not super close, but it's not that far away. Okay. And the alarm went off, and it was like 5:30. It was an early evening class. It was like 5:30 in the evening. I was up in the room 255, and the alarm went off, and I looked outside. It was spring. Leaves were on the tree. I looked, and not a leaf was moving. There was no wind at all. And I said, why are they doing the test at 5:30 in the afternoon? They usually do those at 11 o'clock on Wednesdays, first Wednesday of the month, or something like that. Why are they doing it today at 5:30? And in just a few minutes, I can't remember his name now, the night coordinator came up and said, get downstairs. There is a major tornado not that far away. Not a bit of wind here. It was all sucked over there. All the energy was concentrated on Oak Grove. And if I'm not mistaken, it wiped out their whole high school, didn't it? What's that? Oh, okay. So you were in Oak Grove at the time. I bet you that's scary.
Oh, I wasn't.
Oh, you
I
weren't
stayed
there.
like in the outskirts.
I see.
Like it was like how you said it was no wind where I was.
No wind at all. Yeah. It's so eerie. So eerie. Okay. What's that?
That's how it was in this school.
Was it? Were you there?
Yeah, it took the apartments out across the street from me.
Oh wow.
It came, like, y'all know the direction it went, that's what I said. Yeah. Like, it came up Skyland, then it turned and went up 10th Avenue. And it turned and went up to Hargrove. Well, I lived on Hargrove and 10th on the corner, but it took the apartments out across the street from me. I was home. I walked out and it was gone.
It was like a pretty nice day.
Yeah, it was bright. There was a storm that morning.
Yeah.
And the only reason why I was home was because my job in downtown Tuscaloosa had a power.
Oh.
So it went through north, like downtown
Right.
Tuscaloosa. And so I was home for the day, and it just woke up from a nap. And my mom was like calling me, get in your bathtub. I'm like, what's going on? Like, she's like, do you not know anything? I'm like, no.
Just woke up.
I just woke up. It's bright and sunshiny. What's going on? I turned on the TV, and it's on Skyland, and I was like,
Okay. I went to school in Tuscaloosa, we all got out early.
Uh,
A lot of people lost.
yeah, I
Was that
mean,
during the week?
Yes,
Yeah.
it was the middle of the week.
Wasn't it the same hurricanes that went through Pleasant Grove and Hewtown?
oh yeah, same day.
Because
And what's more, you mentioned in the morning, there was a series of much smaller, but we thought major tornadoes that morning that went through. There was an area down 280 before you get to the summit. I didn't know that housing development was over there because trees were there. Next time we drove by, you could see all this housing development. So when did they build that? No, it just took down all the trees. I mean, just make, and that was the vortex. That was just,
That's what they thought
Just
it
the
was.
beginning.
It was just
Yeah.
the beginning that morning, and then here came the thunderstorm.
yeah, and the other ones just dwarfed those, and just all up and down the state. I mean, it usually when there's a tornado, all the weather stations are tracking that tornado. This time they're saying, look, there's so many out there, we're going to try and get the ones that are closest to us. We're not even paying attention to those somewhere else. They didn't have time to do it. Category 5 for destroying Phil Campbell, that's the town I was trying to think of, wiping that out, but we didn't hear about that till the next day. Well, I think we heard a little something, but they were just focusing on the ones that were close enough. And Jerry Tracy, if we get to go there, it's up on Red Mountain. He said they could see the tornadoes passing, because they're way up, they could see them. He said it was so scary.
If you go like down to the old umbrella, the school, you can still tell that the tornado was even.
Really?
Yeah, you can tell like the trees and everything.
Yeah. All right. So quite often associated with intense thunderstorm. There's a picture of one, and unfortunately, I think this was in Dallas maybe. One went through downtown Atlanta too, not the same system, but other times. That's a pretty major storm. You don't want to see that, okay? Boy, that's all they said on it. I do want to go over a little bit more on it. Tornado damage. And by the way here, they show in my book on figure 2317 on page 578, somewhere thereabouts, a hailstorm the size of this one, and they show it here, it looks like to be about 4 inches in diameter. Fell on the thunderstorm in Iowa, damaging automobiles, structures, and crops. Hail can be pretty bad. They're associated with bad thunderstorms, okay? But let's do it on the tornado. They have actually a 6-scale system. 0, 1, 2, 3, 4, and 5, okay? A 0, category 0 tornado, light damage, winds under 75 miles an hour. That's pretty fast, okay? But under that. Damage to chimneys, tree limbs, broken, small trees pushed over, blah, blah. No, category 1, moderate damage. Winds between 76 and 112 miles per hour. Roofing materials removed, mobile homes and moving automobiles pushed around and overturned. Category 2, considerable damage, 113 to 155 miles per hour. Whoa. Roofs torn off of houses, mobile homes demolished, boxcars overturned, large trees snapped or uprooted, light objects become missiles. You don't want to be out there then. Category 3, severe damage, winds 156 to 205 miles per hour, roofs and some walls torn off homes, whole trains overturned, most trees are completely uprooted. This describes Tuscaloosa, okay? Cars lifted off the ground and thrown around. Actually, my wife lived in Huntsville. This was way back. They had one there, and literally they said cars were being thrown. It was at rush hour, and cars were being thrown through intersections. It's just unbelievable. Category 4, devastating damage. Winds 206 to 260 miles an hour. Homes completely leveled, Tuscaloosa. cars thrown, large missiles generated. And in Category 5, incredible damage, winds from 261 to 318 miles an hour. Okay? Okay. And that's, let's see, that's even more than what this one said here. Okay? Homes demolished, swept away, automobile-sized missiles fly through the air more than 100 yards. An automobile lifted up and thrown more than a football field. Okay? Trees not only uprooted, the bark is blown off the trees. Okay? Pretty major stuff. Okay? Now, at our farm in Georgia, all my siblings still live there. It's a strange story. My younger brothers, he lives there, my older brother lives there, my sister lives there. We have a little 2-bedroom bungalow there when we go over, so we'll have a place to stay. But my younger brother's older daughter had just recently finished law school, and she had met a guy from Ohio at Vanderbilt Law School, and they had started dating and they were getting married. And the his parents, was actually, his father was head of pediatrics at Ohio State University's Children's Hospital. I don't remember the name of it. Pretty big dude, okay? I mean, important dude, but nice people, okay? My younger brother is a farmer. He, doctor's son marrying a farmer's daughter. I mean, pretty big. But my brother also works at an electric power company, and they do well enough. He is a vice president for a small electric power company, but he also farms. So they were over, do the exchange of parents. They had decided that was the weekend they were going to come down to the farm and meet my brother's family and see the farm. And so Dan had heard there might be rain later in the day. So he wanted to get them out and show them the farm while it was still nice. So they were out in the field, he was showing them around, walking around, and they were in the pasture where the cows were. And the cows were around and stuff. Dan was talking about something. And just something felt really weird. And they looked around, all the cows had disappeared. I mean, completely. They didn't know where they went. They were there, and then they weren't. I said, what is going on here? And heard sort of a roar, and looked across the field at our neighbor. Used to have a dairy. The dairy was defunct by now. And there was a tornado tracking across the field that was part of the...
And the cows ran?
And the cows had already moved out. They felt the pressure difference. They headed for shelter. They were gone. They had more sense than the people. Okay. And of course, they were already out of the vehicle. It's not safe to be in a vehicle. Here, the chief of pediatrics and his wife and their family went into a ditch in the middle of a cow pasture to get as low as they could go and to be safe while the tornado passed. And that was a Category 0 storm. It doesn't quite match here, but they cut a swath of trees. It didn't uproot them, it just twisted them, killing them,
Is it like what those things are called? The devil?
Oh, a dirt devil type thing, sand, yeah. It's like that, only bigger, yeah.
Oh, it's bigger.
Yeah, but bigger. And it was enough that it cut through now. At the dairy, they had a big old house there, one of the oldest houses in that part of the county. And it was damaged enough it was not repairable. So it's been torn down. Fortunately, my older brother, he married the daughter of the dairy, and they had lived there while her mother was still alive. And once her mom died, they moved out of the house because the house technically belonged to my brother's wife's brother, who was one of my brother's best friends. But because the house belonged to him, he said, okay, Mom's dead. Y'all move out now. Okay, sort of done. So they had moved out like a week before or 2 weeks before, and then the tornado came and destroyed the house they were in. They had been living in just a couple weeks before.
Wow.
Didn't knock it down or anything, but did enough damage it was not repairable.
Wow.
And there literally are paths across the yard. Bianca was mentioning, you can still see where the trees are down. You still see that path where the tornado came. Went right up past my mother's house. She was in the house at the time. It did enough to take some shingles off and twist, tore out about half of a huge magnolia tree right there in her yard, and somehow curved around the house and completely demolished my dad's shop building in back. Concrete block structure, and they still haven't found the roof of that. And this was a Category 0 storm. And a lot of the blocks they found way down in the woods. Unbelievable for a Category 0 storm, okay? I can't imagine what it was like in Tuscaloosa, Phil Campbell, the other places, Harrisburg or something like that. It's just incredible. Okay, I think I beat that. Okay. Now let's move to hurricanes. Hurricanes have classifications too. They start as tropical depressions, which are basically low pressure areas, a lot like a thunderstorm, except the big word here is tropical. They start in the tropics. Now the ones that affect us just about always start off the coast of Africa, somewhere between the equator and the Tropic of Cancer, usually up here, and they move as the prevailing easterlies. They move across, almost always picking up speed and strength, and then when they start getting close to the landmass of South America and some of these islands, they tend to twist and bend. Sometimes they make it into the Gulf of Mexico. If they do, stand by, there's going to be damage, okay? Either in Mexico or down here or in the southern U.S. A lot of times they make their way up here. There was one year, I don't think that was the same year that Katrina hit New Orleans, but it was one of those years. Florida had been crisscrossed by about 4 tornadoes that year. I mean, they come this way and come that way. I mean, it was just really a very active year. It may have been the same year. The year of Katrina, you know how they start naming the storms with A, B, C. Now, it used to be in the old days, they were always named women's names. I can't imagine why. Okay? Huh?
Yeah, like a
Yeah, exactly. But nowadays, it's every other storm is male, female. They do it. So you'll notice that. But it used to be, and what they used to do, literally, is what I heard. I don't know if this is true. The meteorologists who worked at the National Weather Center or the Hurricane Center or wherever it was, they would name them after their wives. Okay, so it was even more personal, but I don't know if that's true or not. Yeah, I think they may not have supper that night or something, I don't know. But anyway, then they started naming them alphabetically women's names, but then they started alternating. Because remember, Ivan hit the Gulf Coast one year, not the same year as Katrina, so every other year, and they'll reverse them. Like last year, if they started with male, this year they'll start with female, with A, and they do like that.
But where did the name come from? It was like, you know what, this looks like a hurricane, but is that how they do it?
I don't know who does it. Someone. I bet you they've already named the storms for the next 5 years.
They already
or
have
so.
names,
Yeah.
just waiting.
Waiting for the storm to happen.
Yeah.
They need to know one Brittany.
What's that?
They need to know one after her.
We might have a Brittany next year.
Who knows?
Yeah.
I can see that.
And they may even have a Terry one year, you know. But that year of Katrina,
Bad for me both.
that year of Katrina, I don't know if you remember, later in the year they had Rita. They got up to R's. And guess what? Before that season was over with, they had made it all the way through the alphabet, and it started naming them A, B, B, C, C, not even the names. because they just didn't have names picked out past the end of the alphabet. That was one of the most active years ever on record. They went through at least 26 names, 27, 28, something like that. And they don't name them until they're tropical storms. They don't name tropical depressions. So what the tropical depression is an area of low pressure. Remember, the low pressure is the one that causes its cyclonic activity. Okay? The winds are generally moving 55 kilometers per hour or less. That would be about 36 miles per hour or less. Okay? When they move up greater than 56 miles per hour, it becomes kilometers per hour, then it becomes a tropical storm. More intense, low pressure area, and guess what? These go hand in glove. The larger the drop in pressure, the more rapid the wind. So that's why technically they're measured by the pressure, but they usually refer to the wind. Okay? 120 kilometers per hour would be 72 or 75 miles per hour. Okay? So that's getting pretty high. The hurricane, very intense low pressure, and there is a millibar reading for that. The winds are in excess of 75 miles per hour. Fully developed hurricane has a calm eye surrounded by an intense rain and thunderstorms, and they actually call the outer part of the eye the wall. And if you're inside the eye, you feel almost nothing, very low pressure, but you can look and see that wall of water just doing like this, and there's hardly any wind at all inside the storm. It's really bizarre. I had a friend, he was an undergrad student when I was a graduate student at University of Georgia. He was a forestry major, no less, but his dad had been was a pilot for Eastern Airlines. And Doug found out he really loved flying better than he loved trees. He liked trees a lot, but he really loved flying. So after he graduated, he went on, and I guess he may have already been a pilot, but he went to apply, but they weren't hiring at the major airlines. That was when a lot of airlines were folding and consolidating, and there were more pilots than they had. So he went to work for the NOAA, National Oceanic and Atmospheric Administration. And his job was to fly into the middle of hurricanes and take measurements.
Is your friend insane?
Huh?
Is your friend insane?
No. You fly over the top and then sink down into the eye. And it's pretty calm. It's just getting across the wall. And if you go high enough, you can usually do that. Okay. Yeah, he was a little. Yeah, to answer your question, yeah. Okay. Seemed like to me he was. But he did that for several years and then got on with the airlines. So he wound up, I think, flying for Delta. Because I think Eastern collapsed. I know they did at some point. And so he flew for Delta. And then, actually, surprisingly, he had a heart attack at a fairly young age. So he retired. So I haven't heard much from him since then. Nice guy, though. So, okay, I think we've covered all that. Let's see some of the graphic on this. Okay, that's a picture. I think this may be Andrew, maybe? John, Hurricane John. I don't even remember what year it was, John, but you can see the eye in the middle, and if you were in there, it'd be calm as it could be, okay? And right at the wall here, the winds are so fierce, it's just unbelievable, okay? And then those extend, whereas a tornado is a miniature of this, not nearly the region, but much more intense than the hurricane. Not total energy-wise, but it's really, really intense. So this is giant, and this can cover, whereas a tornado up to 400 meters, which is about a quarter of a mile, maybe up to a mile in diameter. This thing is hundreds of miles in diameter. I don't know what this one was, but they cover. In fact, when you have them in the Gulf of Mexico, they almost cover the whole Gulf. I mean, it's unbelievable. Okay, here's what's happening with it. It's a lot like we saw in the thunderstorm, only way more intense, and the eye is completely open. Okay? Now this will be in 3 dimensions. We're only seeing 2 dimensions here. The eye, that's where the lowest pressure is, but it's still as it can be. Just like we said, not a leaf moving, but this would be out at sea, not at land. But those things are out. So what's happening here, remember the thunderstorm, you had the convective movement up. This is on either side here, it's convective movement. And the whole thing is the twisting movement. That's the Coriolis effect. But the eye in the middle, nothing happens because that's the still part. And since it's such low pressure, air is sucked down into the eye and then fed up through the wall. It's just a mess. And usually the eye is perfectly calm. You have hurricane force winds within a certain distance. They show here from maybe 15 to 50 kilometers out. You have, this is one. The maximum winds are right near the eye, and lots of rain. And then the hurricane winds are out there, and then you have gale force or tropical storm winds outside that, and then tropical, it goes down for this. Lots of activity. Now, since they're in the tropics, they're always sucking up more energy, more heat, and they just can maintain and actually grow, and they sometimes reduce in size too. But remember Katrina? It was a Category 5 until just before it hit. Fortunately, it dropped to a 4. Who knows what would have been the damage then? But boy, so much of Louisiana. What's that?
One probably been gone if it was
Yeah, it was amazing. Okay. Now, wow. That was it. That's all they're going to do. However, they do have a table here. I wanted you to compare these tables. Okay? Hurricane damage. Now, tornadoes have 6 classifications, 0 through 5. Hurricanes have 5 classifications, 1 through 5. Anything less than a 1 is a tropical storm. Less than that is a tropical depression. Okay? So here's the minimal hurricane, Category 1. Don't think it's minimal. Just like the Category 0 tornado can still do a lot of damage. But a Category 1 hurricane is 75 to 95 mile an hour wind. If you look back to your tornadoes, that's basically just about a Category 1 tornado too. Okay? Just tornadoes go a little bit higher. Category 2 hurricane, 96 to 110 miles per hour. Well, that's the stronger Category 1 tornado. Category 3, 111 to 130 miles per hour wind. That's a weak Category 2 tornado. Category 4, extreme, that would be 131 to 155 mile an hour wind. That's just a strong Category 2 tornado. And the Category 5 catastrophic hurricane is over 155 miles per hour wind. That's a Category 3 tornado, a Category 4 tornado, and a Category 5 tornado. They keep growing after that. Of course, they're very localized, very small area, whereas hurricanes, huge areas. So hurricanes pack more punch, but not in the immediate area. Okay. All right. The next, and I think it's the last section, is it? No. It's the last section of weather. We've still got climate to go. The climate's the shorter half, okay? Weather forecasting. I've already hinted on this a little bit too. Based on mathematical models of the atmosphere. Now here's the problem, folks. What is the atmosphere? It's all that coating of air around the earth, right? How big is that atmosphere? Say again? Okay, not quite that much, okay? We don't go all the way to the sun. Oh, good deal. Thank you.
You got the
okay? But it goes miles up, okay? And then it covers the whole area of the earth. And if you think about it, it's this huge, very complex thing. So how in the world are we going to model that mathematically? Well, we've got to have data points. So what they do, I hope I'm not exaggerating this, I think that in a few areas of the country, maybe 20 or 50 or something like that, they send up a weather balloon 2 or 3 times a week and take data measurements from that. Okay? Now, they also have planes that fly around and take data points. But there ain't enough planes going that you can measure the whole atmosphere or anywhere close. And a few weather balloons are just going to get really, spatially and time-wise, just a small thing. So they're making mathematical models off of almost minuscule data. Okay? So how in the world can they get very good? They have done incredible. But they do these, and then they've got to get all the interactions going on. They're measuring wind speeds, they're measuring temperatures, they're measuring vortexes, they're measuring just an unbelievable humidities, unbelievable thing. So to enter these models, which are really complicated, literally billions of calculations are necessary, and you have to use supercomputers. If you tried to do it on a laptop, the 7-day would be over with before you had the forecast for the next day, okay? No way to do it without supercomputers. That many calculations off very few data points. If you got more data points, they don't have the computer capacity to process them. So it's really just a guessing game. Intelligent guessing, but it is. Fairly accurate forecast up to 3 days are possible. The 7-day forecast, there's an old saying it's like spitting into the wind. I mean, you hope it's not going to come back and hit you. You know, we don't know. But the thing is, only pay attention. In fact, most of the time we only pay attention to what's happening tomorrow. Yeah, I'll pay attention to say what we think it's going to happen in a week, but by the time the next week, I've forgotten what it was a week ago. And it doesn't matter. It didn't matter even then. Only about 3 days are you fairly accurate. They may do a little better than that sometimes, other times nowhere close. Major uncertainty, insufficient technology to connect the small to large scale events. Okay? Those weather balloons are measuring very, very small scale, right around the balloon. The airplanes may be a little bit bigger scale, but they only can stay up so long, okay? How do you tie those very small, distinct measurements and tie them into a model that covers the whole atmosphere? It takes billions of calculations and still not very good. Ultimately, oceanic influences need to be better understood. Before we can understand the weather and the atmosphere around us, we need to understand the oceans. And guess what? Some people have claimed, I don't know if this is fair enough or not, we probably know the moon better than we know our oceans. We almost know Mars better than we know our oceans, because we sent up things to Mars and they've been tracking, sending back data for a long time. But we know close to zilch about our oceans, okay? So we really need to focus a lot closer at home, but they are always changing. So, wow. Tough set of problems here, isn't it? All right, that ends the weather part. It's not half of the book, but half of the chapter, but it's the first portion of it. Now we move to climate. What is the difference between weather and climate in your mind?
Climate, we have it's like the labor effect.
It's like what?
The labor effect or how the weather came or whatever.
Okay, very good. Weather is what's happening today. And maybe tomorrow, maybe 3 days from now. It's measured like climate, like you say, what's happened over all the time that we've been able to tell. Climate's a big picture thing. Weather is an immediate, small scale, right what's happening now. Okay, yeah, you hit it really well. Climate is a composite, larger weather patterns occurring over numbers of years, as in decades, centuries, millennia, okay, numbers of years. Climate is a determining factor in a lot of different things, and therefore when we're talking about, and there is a fair amount of talk about climate change, okay? Say again?
A whole lot of talk.
I still can't hear.
A whole lot.
A whole lot of talk, yeah, about climate change. And we're not talking something that's happening immediately, but small changes over a long period. It makes you wonder, can we sustain it? Okay, something happened that wiped out the dinosaurs in a pretty, geologically speaking. That first chapter we skipped, chapter 21, on geologic time, you talk about things that are in thousands of tens of thousands of years. That's geologic time, you know. The dinosaurs were probably wiped out over at least decades or centuries, you know, for them all to, whatever happened, okay? Now, so basically climate, we're talking big things. So types of plants and animals at a given location, climate's going to determine that. Now, this is something that really bothers me about climate change. Things are happening way too rapidly, I think, because, does anyone know what an armadillo is?
Yeah.
Okay, have you ever seen one? Okay, certainly you have. Back at the time when I was born, I don't think there was an armadillo anywhere in the Southeast. They were all down Texas, Mexico type area, okay? They have made their way up. I've heard of them as far north as Nebraska. They never used to be in Nebraska, okay, ever in our recorded history. And now they're all over the place here. On the farm, near our, we have cattle, and I just love seeing these. They're called cattle egrets. Big, beautiful white birds that look a little like not a stork, but a heron or something like that. Big, graceful flyers and stuff. They hang around the cattle herds. They're eating the flies that would be bothering the cows. So they're very nice to have around. You don't have to treat the cows to keep the flies off of them. The birds do it. When I was young, I'd never seen cattle eat. And we had cows back then too. That's happened during my lifetime. Armadillos, cattle egrets. Something's going on, folks. Types of plants or animals in a given location. The types of houses built. When I mentioned the Swiss Alps, what's the building you see, the mental picture you see of a building in the Swiss Alps? Called a chalet or something like that. Describe it for me.
It's kind of a log cabin looking thing.
Okay. Tell me about its roof.
It's kind of slanted and it's got
Very slanted. Very steep roofs. Why would they build such steep roofs in the Alps?
so in case of an avalanche.
The what?
In case there's an avalanche, the snow.
Okay, snow accumulation. You don't build a flat roof. Look at every roof on this campus except the Jess Lanier building over there. Every one of them is a flat roof. If we were in any kind of area that got any kind of snow, we would be caved in. So the Swiss Alps, they build them very steep because they don't want any snow accumulating on those roofs. Here in the Southeast, who cares? save on shingles. Takes more shingles to cover this than it would do you to cover that, right? So, save on it, cheap. But you have other problems too, so we finally started putting slanted roofs on. Most of our houses have them, but they don't have to be very steep. Okay. So the types of houses built. Like I said, the sidings in the Midwest, really thick walls for better insulation. And shoot, I remember houses I've lived in probably didn't have much insulation in the walls. Maybe a little in the ceiling. The house we're in now, I don't think has any wall insulation at all. It was built in the 1930s. And in the ceiling, someone added it, but it's pretty thin. I need to go up and put more. What's that? 1930s.
30s?
Yeah. Yeah, my wife
I want
likes
to see
old
what
things.
your house looks like.
I'm glad. Hey, oh, that's funny. Okay. All right. Lifestyles. Who went? Most years, who wins the Stanley Cup? Does anyone know what the Stanley Cup is?
Is it,
Huh?
is it
What's that?
hockey?
Hockey. Yeah.
Oh.
It's almost always the Canadians, isn't it? Why is that?
The ice.
They have ice year round. They always skating.
Yeah. That's
Yeah, it's we don't have very much ice down here, so we don't have. There's not many ice skaters around here. What? Pelham has about the only rink in the area, don't we?
I think Huntsville's got one.
And Huntsville has one, yeah. But in the Birmingham area, I think there's one ice rink that I know of, and that's in Pelham.
Yeah, I went to the one. Yeah, Pelham. And then they just did one at the park downtown.
Oh yeah,
I don't know if it's
yeah,
still there,
Railroad
but
Park.
they did,
Yeah, they did it in the
They
middle of
did it
winter,
for-
around Christmas, I think.
Mhm.
They did one, and they had to freeze like crazy because it was warm. You know? So yeah, our lifestyle doesn't include much cross-country skiing, no ice skating to speak of. We just don't do that. But yet, who has the best football teams? Yes, the Southeastern Conference, Texas, Florida, where you can play just about all year long.
Yeah.
You can't get out and practice football much in Canada. Okay? Maybe a few months a year, you know.
But it's not
Yeah.
that popular in Canada, right?
Yeah, how could it be? Yeah, exactly. Okay? So, lifestyles, I'll just hit on sport, but other things. What does climate influence? It influences the shape of the landscape. We talked about this in the last chapter. Remember the attitude of the rocks? The shape of things? Yeah, that's the climate influences that over time. The types of soil, we mentioned this several times already. Here in the Southeast, unfortunately, our soils are generally pretty poor. Now, there's several reasons for it, but one of the major ones is we have high temperatures and lots of moisture, so mechanical, not so much mechanical, chemical and biological weathering going around year round. And in warmer, wetter times, doubling, tripling, quadrupling the rate at which humus is being eaten up, okay? Whereas in the north right now, those soils are not losing any humus at all. They're under feet of snow. There's not going to be any chemical or biological breakdown until the spring. When it finally warms up, we're doing it all year long. So yeah, there's types of soil. Agricultural type and productivity. What advantage do we have agriculturally over the Midwest? Say again?
Agriculturally?
Yeah.
We have more rain.
Okay, we might have a little bit more rain. Boy, their soil is so rich. They plant their crops like this, we do ours like this because our soil just can't support that density of crops. What can we do they can't do? Double crop. We can put wheat in. In fact, the wheat's growing right now. You can't grow any wheat in Nebraska right now.
Oh.
Too cold.
Okay.
Wheat's growing now. They'll be harvesting the wheat in May, planting soybeans after that. We can double crop here. They can't. They sometimes really sweat getting one crop of corn in. And corn's a fairly rapid growing plant. They just can't do it. I mean, some years, if their spring is too late or the fall comes, the freeze comes too soon, they lose whole crops. Most of the time they can get one crop in. We quite often can get two. Okay? So we might be less productive as far as yield, but we can get 2 crops a year. They can't. Okay? Trees. Bianca mentioned you can still tell around Oak Grove, and this was probably 15 years ago that tornado went through Oak Grove. I'm guessing at least that. And she said you could still see the areas where it went through because the trees are just shorter, smaller, younger. Other trees are huge. But go out west, where there's not as much rainfall and shorter growing seasons, north and west. They had a fire in Yellowstone, and 5 years later it looked like it had just happened, because trees do not regenerate. They have short growing seasons and not that much rainfall. So here, you drive past where the tornadoes went by, yeah, they're smaller trees, you can tell where they went, but they're vegetative all over the place. You don't see the stumps anymore. They're grown over. Agricultural types and productivity, that depends on climate. Okay? Long period of climate, not just the weather today, climate over. So what are the major climate groups? 2 major factors that determine the major climate groups, and I think we've hit on this already. Intensity of the incoming solar radiation. Where is the solar radiation the most intense? The equator. Okay? And what determines that is the angle of incidence. It's where the sun is directly overhead. And where are the only places on the planet where the sun is ever directly overhead, even once a year? The tropics, that's how you define it. Because guess what? In the summertime, the Tropic of Cancer, the sun is directly overhead on one day a year. That would be June 21st or somewhere close to that. And in our winter, their summer, December 21st, directly overhead the Tropic of Capricorn. And sometime in between those times, it's directly overhead twice a year, everywhere in between. The angle of incidence around the equator, within the tropics, pretty direct. That's what makes tropics, okay? That's what makes it warm there, okay? Determined by angle of incidence. Where we live, it's never directly overhead. I think we calculated back several chapters ago, the maximum it gets is like 80 degrees. That's the maximum. It never makes it to 90. It's like 80. June 21st is close to 80 degrees. We never have it directly overhead. So we are always at some angle of incidence, and the angle of incidence, that keeps us a little cooler, generally. Why is that? Because remember, we have this big band of atmosphere around the globe, everywhere. And when the sun shines directly through that, or almost directly, it comes directly through. When it hits us, it comes through at an angle, so it's going through a lot more atmosphere to get to us. It's only going through this much here, going through that much there, because of the angle. That's why at the polar regions, the angle is so small year-round. Even in the middle of summer, the angle is still so gentle, it's really cold up there. Okay? So determined by the angle of incidence. That also impacts the number of daylight hours. We did those exercises too, didn't we? Back in an earlier lab. Near the equator, what's the length of the day? Well, everywhere it's 24 hours, but daylight. 12 hours and 12 hours of darkness year-round. I think I told you about the student I had who was from Kenya. Okay, there's Kenya right there. Sits right at the equator, goes right through the middle of Kenya almost. She said she could not get you. That's the hardest thing. She knew it was going to be cooler up here. She knew it was going to be changes. But she said the thing she had the most trouble getting used to coming to America was that the daylight changed all year round, you know. We'd have longer days in the summer and shorter days in the winter. She said, I didn't think that happened anywhere. Why does this happen? It's because of that good old tilt of the earth, 23.5 degrees. Okay? Number of daylight hours varies. That's all because of the tilt of Earth's rotation axis. Can you imagine what it's like on Uranus, whose tilt is like this almost horizontal? That has to be the weirdest. Of course, no one lives there, so who cares? But that would be so bizarre. Okay? So, equatorial regions receive more solar radiation. Yep. Around the tropics, especially the closer to the equator, even more. The intensity changes on a yearly basis. Okay? But it doesn't change too much. The number of daylight, okay. This is a really poor slide. The equatorial regions receive more solar radiation. There is less intensity changes on a yearly basis, and the number of daylight hours varies very little in the equatorial. Outside the equatorial, the intensity changes on a yearly basis, and the number of daylight hours varies annually. These two should be under non-equatorial regions. The equatorial region, this is almost, it's not constant, but it's very regular, and this is also very little change. Had a friend in high school, his sister married a guy who, I don't know if he was military or what, but he was stationed in Hawaii. Got to find Hawaii, there it is. Yeah. And that's in the tropics. Not far in the tropics, but it is. And I couldn't believe this when I heard her gripe about, of course, I remember her, she griped about anything. And she said, yeah, but the weather just never changes. It's always 72 degrees. I said, oh, shucks. What? Give me that anytime.
Nice. What
Yeah.
you whining about?
Yeah, what are you whining about? Oh, some hot days will go up to 80. Well, mostly because you're right, all that water keeps you air conditioned, and they basically have very little.
Ours gets up to 90 in the summer.
Oh, yeah.
That's fine.
Yeah, so give me a break. My younger brother's only son, my only nephew on that side of the family, he was stationed in the Navy in Hawaii for a year or two. And one time he wrote and said, somebody said, well, how is it that, or something like that, he said, well, every morning I wake up another day in paradise. I mean, he appreciated it, that other gal didn't. So, let's see, what is the next slide? The only reason I'm asking? Okay, climate and latitude. That's where we're going to begin next time. I feel like I'm cheating you out of a few dollars of your tuition, a few pennies of you. Where is this? Oh, there it is. Okay. That's where we'll begin next time. I can't do the whole slide in the time we've got left. So that's it. Any questions? Anything we've done so far? So let's talk about Tuesday. Tuesday, we'll come in, we'll finish this chapter for sure. Okay? We won't be ready for a lab because the lab is going to be at the Weather Center. So we will be the last 30 minutes on Tuesday, then we'll have the test from the last chapter, chapter 19. No, 20. Okay? And then I'm going to try to schedule the Weather Center visit for Thursday. Don't know if I'll get it, but I should know by Tuesday if I'm successful or not. So anyway, we'll do that. And then if that day, if we do get to go Thursday, I'm guessing he's going to want us later in the day. So what we may do is have the test on chapter 23, because we'll probably finish it on Tuesday. We may have it before we go to the Weather Center. Okay, so that's what I'm going to figure now. We may have a little bit of class where we leave off, and We may start the oceanography chapter next time and then continue it on. Then I'll give you 30 minutes for the test, and then we'll leave and go to the weather center. I'm guessing he's going to want it like that because he doesn't usually work in the middle of the day. He works later in the day, so we'll probably go that way. Okay? And then we'll move into chapter 24. That's the last chapter. And when we finish that, there's a real quick, just paper lab. And then we will have that test. And then on the final exam, comprehensive. Comprehensive final exam, it sounds pretty heavy. It's probably going to be the easiest test you have all term. Probably take you less than 15 minutes, okay? But it's going to cover everything. So. Good job. Have a good weekend.
Thank you.
And we'll see you Tuesday, if not before. Oh, let me turn this off.